All right. Hello, everyone, and welcome to this live stream where I will go through the challenges of the high school CTF competition that we hosted last weekend. It was a Swedish competition, and it's called like Swedish Championships in Security. So yeah, it's a beginner CTF targeted towards like high school students and so on. So yeah, in this stream I will try to go through most or all of the challenges. We'll see a little bit if we do this in one session, or like if we split it up in multiple sessions or whatever. But yeah, so feel free to post stuff in the chat if you have any questions or additional insights or comments about what's going on, and I will try to, take that into account. Yeah, so this was the website. So the competition was, a lot of the stuff was in Swedish, but I will do this all in English, and I will translate whenever is anything relevant. I think we tried to make most of the important stuff in English, but for a few challenges that's not true. So there was a whole bunch of challenges in your standard CTF categories, forensics, crypto. We had this introduction category, which was just like showing some of like the basics of CTF. So like how you submit the flag and so on. So we'll look at that. And then we had some miscellaneous problems and some potables and some web challenges and some reversing challenges. So let's actually just quickly start with these introduction challenges, because I think that makes most sense. So yeah, so the first one, let's see, I just need to make sure that we have everything that we need. Oh yeah, also I should add that all of these challenges that I will, so the challenges are no longer online on the competition page, but we have released all of the challenges on GitHub. So you can go to, so this whole thing is organized by an organization called CodeSport or CodeSport. So we do events related to like competitive programming and CTF and so on, for like targeted towards people in Sweden. But anyway, on our GitHub organization, we have released all of the challenges, all of the source code, Docker files, and so on. So you can just like download this and try all of the challenges on your own. And there are like for the challenges that require backend, there's like a Docker Compose file, so you can just very easily run it yourself. And I will show that. So yes, as I said, let's start with the introduction challenges. So the first one is basically just explaining what a CTF is. So, to capture the flag competition, you're looking for a specific flag in each challenge, and they typically follow a specific format. In this case, our flags follow this SSM format, and then you're supposed to get that and submit it. So, oh yeah, I will not be actually submitting the flags here, but I'll just show them. So in this case, they will just give you a flag so you can try to submit it to just see that you understand how the web interface works. So your standard like intro challenge. Then we have the actual intro challenges where you actually learn something. So we have this ELF 101, and this is a challenge that explains like the ELF format, and it's like the equivalent of an exe file on Windows, and it explains, because like as I said, this is targeted towards beginners, so you know, we don't assume like knowledge about all of these things. So it explains that like to be able to run an ELF file, you need a Linux system, and you can either do like WSL on Windows, or you can have a virtual machine, and there's some references on how you can install that. And then the challenge is just to we're given this ELF file, which we can then just run, and we get a flag. So that's just an intro challenge to like get people familiar with ELF binaries. And then you have the encoding 101. So in this challenge, you're given like a hex encoded string, and it talks about this. The description here talks about like hex encoding and so on. So you're given a hex encoded string, and here they have an example where like hello world hex encoded will be this. So here's an hex encoded string. Try to decode this. So we can, for example, use. Let me just increase the font size a little bit. We can use Python to decode this, and we get another string like this, which is a base 64 encoded string. So we can decode this with Python as well in the base 64 library. It's also good to spell correctly. Decode. And then the flag is 37 base 85 what. So there you have a flag. So this is also again just an intro challenge to teach about encodings. And finally we have the remote 101. So in this challenge, it just explains that for some of these challenges, you need to communicate with the challenge over like a TCP connection. And one way to do this is to use netcat in your terminal and connect to a server and communicate with it. So it just explains that a little bit. So we need to connect to the server to get the flag. So this is a challenge where you actually have a backend, which means it's a good opportunity for me to show what you do if you want to try these challenges on your own. So we have these all these directories, each for every challenge. And if we go into this intro remote, you'll see there's a Docker compose file, so you can just run Docker compose up and let that run. Let's see, there was some kind of error. Maybe it was some like am I having some like DNS issues or something? What's inside this? A bit embarrassing that I'm supposed to show how simple it is to run these on your own, and then it immediately does not work, of course. Failed to fetch. What? Yeah, so suggestion in the chat. Outdated apt cache. Suggest to clear your Docker cache. Yes. That's annoying. What if I just build the well, yeah, but I mean, I can run, of course, I can run apt update like in here, but that wouldn't explain why it's failing inside. I mean, here it's obviously working, but this wouldn't explain why it's failing inside. Or is it? Yeah, and I mean the Docker file is running apt-get update, so this should not be an issue. Yeah. Yeah, I would probably need to just clear this out. So let's see. Docker images or let's see. So the issue here is that yeah, there's probably some old cached thing when Docker is trying to build, and yeah, it's not working out well at all. So can we just okay, so let's see if this yeah, this seems to be working better. So there was something with the Ubuntu Docker image there. Maybe this was related to the OpenSSL bug that was just released. So maybe they removed the vulnerable version from the package repository without, and then that was cached on the in Docker. So yeah, exactly. I mean, this this will not be an issue for you. So if let's pretend you didn't see the past few minutes, and whatever, like the only thing you need to do is you go into the directory of the challenge, you run docker compose up, and you get something like this, and now the challenge is running. So if we go back to the description of the challenge here, of course, in any challenge where an IP address is listed, this will instead be localhost because it's not the remote servers anymore. So, and that's also like, if you look in every challenge will have this challenge.yaml file, which contains all like the metadata for the challenge, and you will see there's like a service with a container. So this is running. So now we can just run netcat to localhost on the port 50,000, and then we get a flag. So yeah, then now we have managed to get through the setting up one of the challenges locally and connecting to it, and we've solved this remote one-on-one challenge. So, and then like to shut down this, we just press Ctrl C and wait a little bit. You can press again to like force it, but that's unnecessary, I think. So we'll wait a little bit. Yes. Let's close that. All right. So that's the intro challenges. So where do we start? Should we go just top to bottom? Start with the forensic challenges. Forensics. And I think we will do this in the in the point order. So these numbers was like how many points the challenges were worth. So let's start with this challenge, Datorer AB, which means like computers Inc. or yeah, something like that. So a forensic challenge. So in this challenge, they say that this company, they have had a breach, and you're supposed to figure out what was stolen. And then there's this PCAP file. So let's go into forensics. And then in each of these directories, there would be a lot of files, but some of them you're not supposed to have when you're trying to solve the challenges. So the way you can easily check, like if I want to try this challenge in the way it was presented to the contestants, we can look in the challenge.yaml file, and you have this downloadable files, which corresponds to files in this directory. And you see also that I run, instead of just doing cat challenge.yaml to show all the contents, I do grep-v flags. And this will basically print everything in the file except the flag. So this means that I'm not there are no like spoilers, or like I'm not biased by knowing the flag before trying the challenge. So that's another trick you can do if you're trying to solve these on your own. So we have the challenge.pcap, which we have here. And what I will do... No, actually, it's not native for this challenge. For later challenges, when we actually need to start like writing scripts and stuff, I'll just copy that over to like a separate directory, which will be my like directory where I'm solving stuff. But for now, that's not needed. So a pcap file is like a set of recorded traffic. Typically, it's network traffic. But you can also use Wireshark to look at, for example, USB traffic going from like a computer to a device and so on. But mainly it's network traffic. So if we have Wireshark, we can open this file. And what we see here is a bunch of packets. So this is like the list of all the packets, and here you can see an analysis of the currently selected packets. So it will show you the different layers of the protocol, yeah, in these columns you can see like the timestamp relative to the first packet, and then you have the source address, destination address, and then Wireshark tries to decode the protocol and so on. So what you can do here is you can go to statistics, and you go to protocol hierarchy, which is interesting. So here you can see the like distributions of different types of traffic Wireshark has been able to identify. So we can see that everything is TCP in this file, and out of this TCP, it claims that like 43% is telnet and some FTP data and yeah, related stuff. So this seems to be some kind of FTP transfer and some telnet stuff going on. So that's interesting, and we will look more into this. Another thing you can do, which is really helpful, is if you click a TCP packet and you right-click it and you do follow TCP stream, you will get the like reassembled connection. Like it will take all the packets belonging to that connection and all the data going in both directions and display it to you. And you can see here that the red stuff is what the client is sending to the server, and the blue stuff is what the server is sending back. So we can see here, and this is stream number 0. So this is the first stream that Wireshark has identified, which makes sense because we took the first packet. So there's nothing before that. So we can see that there is a lot of dots and stuff here, which means that these are things that are not like representable with like a printable ASCII character, so some binary data. You can verify this by going to the hex dump view instead. You see a bunch of different values here. What we see, like, we don't necessarily need to understand like every single thing that's going on here. We can see that there is some kind of data being sent to the server, and the server sends something back. And eventually here you see that there is like a login, and it seems like so here we can also see that the server is like echoing back the characters that you type. So the client sends a V to the server sends a V back to the client, and so on, which makes this like a little bit annoying to view. So what you can do is change so that you see only one side of the conversation. You can see that here you get a login prompt, and someone logged in with a VD, which is Swedish for like CEO, and then there's a password prompt, which is not echoed back, but if we go back to the entire conversation, we can see that the password is summer 2021, and then you get the standard Ubuntu welcome banner thing, and then you can see again things being echoed. So they are running ls, and you get some stuff here, and then you can see. So actually, let's switch back to the server only command. So they run ls, and then you have these things which are like ANSI control characters to do the colors and stuff, which is also a little bit annoying. But we can make out things like cat pictures, production ideas, vacation pictures, and so on. And then they do ls inside of these. And we can see that there is flagship.jpg, maybe interesting. And then you can see that they are running zip. And they seem to be zipping up all of these files. You can see here, like adding all of these to the zip file. And they also do zip with an encryption -E, and then here it says like enter password, and this is not echoed back. But if we switch back to the mixed view, we have a password here. So actually, let me just open up an editor for just some scratch notes. So let me save this password. Go back to Wireshark. Okay, so we have the password that was used for the zip file, but we don't have the zip file itself. Let's just increment this down here and check the next stream. So here we see part of an FTP protocol conversation. So this is part of the FTP protocol. And basically what they're doing here is that they are logging in again with the same credentials, and then they're setting up like the IP addresses and ports and stuff that would be used for transfer. They list files, and they will download the x.zip file. So again, we see that the x.zip file was downloaded, but we don't have the actual file itself. And then we go to the next one. This is also related to the FTP data. That's the response. So the FTP conversation actually works on like, you have two
instead of having everything like in-band on one connection, you can have like two connections. So you're like sending commands on one and you're getting the results back on the other one. So this is the response to the file listing command that was sent. And then the next stream here we see something that's like not human readable, but important stuff. We see that it starts with PK, and we see this like cat pictures and like these file names and so on. So this is the actual zip file that was transferred. So what we can do here is we can switch here from ASCII to RAW, and now we have to be a little bit careful. You have to see, wait here. Down here it says like it was like number of packets that belongs to this conversation, and it was ticking up because it was like analyzing through the traffic to like reassemble the whole stream from all the different packets. So I need to wait until this has stopped ticking up, because if I would just switch to this, because we want to save this whole file. So if I would have very quickly clicked save as before this one has like settled, I would actually not store, like Wireshark will not actually wait for this to complete. It will just store whatever it has decoded so far. So you would only get like half the file or something. So you wait until this has stopped increasing, and then you can click save as, and we call this x.zip, and we save this. And we see here that it's supposed to be, so first of all, you see this is a one-sided thing. So it doesn't matter if we choose entire conversation or only one side. And it's supposed to be 2,105 kilobytes. So if we look here again in the terminal, we have this x.zip, which is 2.1 megabytes. So yes, the file is correct. And if we run file on it, it is identified as a zip file. So actually, let me just make a temporary directory and move that one into it. And then we try to unzip this, and it asks for a password. We copy this one, and we'll unzip everything. And we can browse this. And you get the flagship, and this is the flag. And we can verify this by doing cat on challenge, and you see here that this is the flag. So that's how you solve that. So we close this down, close this down, close this one. So that's some basic Wireshark usage. It's like a very, very powerful program, and it's very good to learn. And a good like companion program is also T-Shark, which I think stands for like Terminal Shark, but I'm not sure. But basically, it allows you to do a lot of these things like from the terminal. So you can script things like if you want to extract stuff programmatically from a PCAP file, you can do this with T-Shark. So that's a nice. It's what I usually find myself doing is like I open it Wireshark to do like a manual analysis, and then I realize that okay, I need to extract all of these things, and then I put that into T-Shark, for example. So that's one way you can do it. All right. We have next challenge, PDF Padlock. So let me update the status. So PDF Padlock, yes. Forensics, PDF Padlock. And then we check. We are given the login.pdf file. So let's see. This is a PDF document. So let's open this in a PDF reader. And let's see if I can put this in like a full... No. Is it like presentation mode? Yeah. So we have a PDF file like that looks like this. And if we click buttons, it looks like we're typing things into the this login thing. And so how is this implemented? Because I mean, like, PDF files like this doesn't seem like something you should be able to do in a PDF file, right? But actually, you can see here that the PDF file consists of 46 pages. And for every page, you see that there's like a different number of characters in each one. And then there is this one, good job, lol. So what happens here, if we have this up while we're clicking, we can see that when we click this, we jump around to different pages. So this is like, these buttons are actually links to different pages. So this means that we probably need to find a sequence of button presses that starts from the beginning and takes us to the, where was it? Around. Okay, there's an incorrect as well, which makes sense. So if we click, maybe that's not implemented. I don't know. But anyway, we want to go from the first one until we get to the good job one. And I think the actually easiest way for this one, let's see if we can just open this one in Chrome instead, because, or maybe that was the, was it Firefox that we want to open this with? Yes. So I don't know if it's fully visible, but if you open the PDF in, for example, Firefox, and this works in multiple PDF readers, but I'll use Firefox as an example, you'll see that at the bottom left here, like as usual, when you hover about a link in Firefox, it will display a preview of where that link's going. Of course, since this is not a web page, so it's not a full URL, but instead it's like a reference within this PDF document. And you can see that like all of these buttons point to the same, it says 33. If we click one of these, we go to page 30. So maybe there's like some indexing that's off or something. But if we hover above, for example, the S button, you see that it points to a different page. So like all of these other buttons, they go to the same page, except the S button, which goes to a different page. If we click that one, and actually we now need to keep notes separately because we don't know what we actually put there. So we put an S. There's a comment that this unfortunately doesn't work on Chromium-based browsers. No, so I mean, this is dependent on your like what kind of information your browser displays. Of course, you can always just click and see which page you land on, and then go back and then click again, and so on. Or you can go a more advanced route and like actually, you know, take the PDF file apart and see how it works. But that's too advanced for what we're doing right now. So let's just continue this. So we have again like everything's pointing towards 17 except S pointing to 8. So that's good. And then you know, we can look around and we see that so M points to a different thing. So this makes sense. Like it starts with SSM, like the flag format. And then like we can just guess that it's going to be a like curly bracket. Yes, because that's the format. So now we kind of have an indication that we are on the right path, right? So, you know, we can just, I guess, do this. And I'm probably not going to do... So here you have Q is different. So put that one. And then you can continue like this. I'm going to cheat a little bit and check what the flag is, just to see that, you know, so QWERTY, so it would be this, and then a 3, and then like RTY. And you see this one is still different. T Y less than, and then you have the S, then V is different, and then it was a 0, which you can see is different, and then R A, right? Yeah, and then a K, and then a curly bracket. And, or did I go wrong somewhere? Oh no. Oh. Oh, you're supposed to press enter. Okay, which page was I on? 16. Ah, right. Of course, you need to press enter once you typed your password. Silly me. Yes, and then we get the good job. It all. Oh, that's also how you get to the incorrect one. Like if we go back to like page 1 and we do like whatever we want and we click enter, it's incorrect. So yeah, that's the way you solve this. You can just do it manually. But there are, of course, you could also just like actually parse the PDF file and the structure and so on, and like do this fully programmatically, which is also an interesting challenge. So yes, let's close this down and move on. So we have Mr. Robot. Here, we have a description where you have a strange file on your desktop. Where is it from? Is someone trying to send this from you? And this was one of the sponsors. We had some sponsors for this competition. So some of the sponsors provided challenges as well. So this was one of the sponsored challenges. I think the computer, the PCAP file was a sponsored challenge as well. So we have this file, yes. And now we don't have any kind of file extension or anything like indicating what this is. So we run the file command on this, and it says that it's a 7-zip archive data. So actually, let's create this directory and just copy the file in here. Okay, so let's use 7-zip and extract this. And we have another file called robot. Let's see what that is, which they claim is a JPEG image. So just rename it to robot.jpg, and then we can look at it. Okay, I mean, it's a nice image, but doesn't seem to be any flag or anything here. So what we can do now is we can use a program called, okay, there is definitely a JPEG image in this file, but maybe there are more things in this file. So what we can do is, first of all, I mean, as I said, we ran the file command to identify that this is a JPEG image, but you can run another program called binwalk, and binwalk is like file but like super powered. and it will not just check like the beginning of the file. It would like go through the whole file and try to find like any types of file contents and stuff inside this file. So if we run this, we see that it's still only a JPEG image. And by the way, we should definitely do this on the original file as well. And it claims that this is still just a 7-zip archive. So yeah, so there could be so when you have a file like this, there are like two main things you want to consider. There could be some data like in the pixel data, like inside the image itself, or it could be like inside the file structure of the image file, or like after the image file. So what we can do is another thing we should actually do is we can run the strings command, which will look for like human printable strings. Of course, this will give like a lot of false positives, but you can like pipe it to less so you see you will get a whole bunch of stuff which just happens to be human printable. You can actually increase like the minimum size. Oh, this is interesting. So here it says lame 3.1 or 3.10, and lame is an audio encoder. So, and also here it says find the flag, by the way. So, you know, why is there something related to audio, and why is this find the flag string showing up inside an image? That's very interesting. And again, you see like lame. So what we're going to do is we're going to open up this file in a hex editor. So this is my favorite hex editor, 010 editor, which is super nice, and I use it for a lot of different stuff. But let's go to the forensics of this thing and separate file. Let's open this. So what it did now was that it automatically identified that this is a JPEG file, and it applied this like file format structure. So it has like parsed the file and will give you like a structure of the contents of the file. So for example, here you can see that like a JPEG file start with this like FFD8 bytes, and this has color, and you can click all these things, and it's like a whole tree structure, and you can analyze this thing. And it's like super nice, and it's super useful, and you can use this to like modify files and analyze files and so on. But what's interesting here is that at the end, you have the end of file marker. Okay, cool. But then it continues. Like there's more stuff here. And this is things related to, as I said, like UID 3, or sorry, ID 3, which is like the name of like the metadata system for like audio files, or at least MP3 files and so on. So like we have a whole block here of data which does not belong to the JPEG file. So we can just copy all of this, open this in a new file. No, that was wrong. That was right. So we take that end of the file, and we copy it to a new file, and we save this, and we call it like robot.dat, because I mean it looks like an MP3 file, but I'm not like completely sure yet. And then I'm gonna run file on this, and it says audio file with ID3 version, like MPEG ADTS layer 3. So this is an MP3 file, if I'm not mistaken. So we're gonna rename this from robot.dat to robot.mp3, and then we are, let's see, can I get some sound on? And let's start by just opening it in VLC. Let me adjust the sound so that maybe I'm not hearing anything. Okay, I don't know. Maybe my configuration is incorrect. But let's skip that step and just go directly to opening it in Audacity. So we open this in Audacity. Audacity is a audio like recording, editing, mixing program. And here you have the audio file. Why? Sorry, I need to check. Oh, you can hear it. Why am I not hearing this? It's super strange. I also want to hear. How would that even work, by the way? Oh, I know. I know why I'm not hearing anything. Okay, now I'm hearing it. Yeah, it sounds like I mean, you can hear it. It's like some very metallic, high-pitched sound. So let's do some things that you can do with sound. When you have something like that, well, first of all, before we start like manipulating the sound, so here you can see like the waveform, but we also want to look at the spectrogram. So we can do this. And yes, we didn't even have to go further. I was going to talk about like... Wait, you said now you're not hearing it. Hold up. I really need to look into my audio setup for like within the VM. But anyway, you heard it before. It's like some metallic sound. So as I said, like the first thing to check is the spectrogram. So this view is like the waveform of the file. You have time on one axis, and you have like the loudness on the other axis. So this is like what it looks like. You can zoom in, and you'll see, you know, many thousands of movements per second. But the spectrogram is a different type of plot. It will say you have still time on like the x-axis, and then you have frequencies on the y-axis, and then the color intensity is the strength of that frequency at that moment in time. So if you would have just like one, like a sine wave, just one single frequency, you would get like a white line going across like this. So here they use this to like draw a picture in the spectrogram. So you have here the flag is audio, text is fun. Yes. And let's just then check, of course, with the challenge.yaml. Audio text is fun. Yes. Okay, great. So that's a little bit of like file format stuff and audio. So let's close this. Okay. Let's go to this one, strange sound. Okay.
Okay, so in this one, we're given this sound file. And let's try to play this. So I'm hearing this, but of course now you are not. I can see this in the mixer. Let me quickly figure out why. This doesn't make any sense at all. Oh, maybe I should switch this to this one. Right, now you should be able to hear it. So you have this beeping sound. Quite annoying to listen to. Yes. So again, let's open that in Audacity and just look at the shape of this. Okay, so this is what it looks like, and the first instinct here could be something like Morse code, but we can fairly quickly rule this out since we have like multiple like we have more than 2 different lengths of these pulses, so that's not Morse code, but it kind of looks like these pulses are they have some kind of common length. Like it looks like this one is half as long as this one, and maybe this one is like 3 times this one, and so on. So there seems to be some kind of, I mean, there's definitely some structure here. We see that, and we can also look at the spectrogram. And here you have this behavior that I just talked about. You have a single frequency, which is just like turning on and off at different intervals. So what we could do then is to like convert this into a sequence of ones and zeros for just on and off. So if we could find a kind of like a grid that we align this to, and then we could think of like, can we map these pulses to like ones and zeros? So here you would have, it looks like this would be like 1 0 1, like, or maybe even, I mean, it's kind of hard to tell with this resolution and stuff, but actually let's switch to the waveform here. So for example, here it looks like you have 1 0 1, and then 2 zeros, and then 2 ones, and so on. Yeah, hello Q3K. Very timely of you arriving when I'm like about to embarrass myself on like signals processing stuff. So yeah. Yes. So I mean, we could of course do this by hand, but like it's not that long, but it's really boring, and
error prone. So hopefully we would be able to do this in a more like intelligent and automated way. So I'm just thinking about here if I should try to do this like completely by hand, the way. So this was one of the challenges that we presented during like the closing ceremony of the competition. So I mean, I definitely know one way to do this. I'm wondering if I should do that or if I should try the other thing, which would be to use like GNU Radio to do this. That could be a fun exercise, but I'm not actually completely sure how I would do that. So have I even installed this? I have not, but we can. Yeah, so a comment from Q2K, but it's not a real DSP challenge unless you stumble through it and have no idea how we actually managed to do it. Yeah, that's very true. And this is definitely an area I really want to be better at, but I'm not really. So let's try to do it with GNU Radio, because that's like, it's nice and fun and visual. So I wonder, how can I just install this from? Is this in the package manager? Search GNU Radio. It is. Let's try this. So let me explain. So GNU Radio is like a full like framework, toolkit, whatever, for working with signals. And they also have this nice program, GNU Radio Companion, where you have a nice like visual programming environment where you it's like a block-based programming thing where you put like different transformers and then you connect them to each other, and you can build your signals processing setup with this. And then if you want, you can generate Python code from this that will run for you. But that's that installing. So let's Google a little bit in the meantime. So what we want to do is like, we want to do like a clock recovery here. So we need to find this this grid that this signal is working on. So we want to say that like this is a 1 and this is a 0, and not like measure like this and be confused about whether this is like a 1 or a 0. So we want to find these imaginary grid lines that this signal is aligned to, and then within each cell of this grid, we can just say like, is this mostly on or mostly off, and then we will have the solution to this. So, and so I think that's what we need to do. So yeah, the manual decoding thing is like, that's very possibly the what I will end up doing if I fail at this. But I think since this signal is so nice and clean, like there is a possibility that we essentially could just you know, put something very simple like this together and it could work. But if I fumble around too much with that, I will just resort to running a small, like trying to write a small Python script. So, or even just take the reference solution, explain what's going on, because I would do basically exactly the same thing. So it's a little bit slow downloading for some reason. Yeah. Time for a drink. Yeah. And by the way, I made some slight adjustments to my streaming setup here, like showing the chat on screen and like adding this like view count and stuff. So, you know, try to be like all the cool streamer kids. But yeah, please, you know, if you have any comments about like, is it useful? Is it annoying with like the chat, for example? Because like you also have the chat on the side, but you know, some people said that if you're watching it in full screen, it's nice to have the chat on screen and so on. So yeah, you know, or feel free to comment on that, or you know, if there would be anything else in this setup that you want, like that I could add or remove or whatever. To be a cool streamer kid, you had to say "What's up, gamer?" and we had to respond Pog. Yeah, you know, I'm not that cool, so you know, we'll keep it. Like, you know, I'm turning 30 like next week, so just moderately cool. Okay, so this is GNU Radio Companion. So this is this visual programming thing. So this, you can connect this to like an actual radio device, or you can work with files and stuff. So we want a file source, and we will pick. Wait, do we have to do some? Actually, yes. Delete this, because a file source would just read the files like raw data, but this is a like a WAV file, so we actually need to decode the WAV file and to get like the actual samples. So let's go with this forensics, and we have this audio file, and we don't want to repeat it, I think. So we apply this, and let's see if this works. So we want this like clock recovery thing, I think, and you also have to define your data types here. So since we have a WAV file with just one channel, we have just like real valued samples, and but in some cases you can also have like complex. So in a lot of like you know, digital signal processing and so on, you work with complex numbers, one representing like the amplitude or value of the signal, and the other one, the complex part, representing the phase of the signal. But we don't have that, and like I'm gonna say, like, I'm definitely not you know, this is definitely not my area, so I'm really, you know, I will be fumbling around here. And we connect these things together, and then let's see what they used in these like examples. They had a binary slicer. What's that? Binary slicer. Slice a float value producing 1 bit positive input produces a binary 1, negative input produces a binary 0. That's, so what does this clock recovery one actually do? Synchronize a signal's frequency, symbols can be extracted. Oh, deprecated. Favor symbol sync instead. Interesting. Symbol sync is a type of symbol synchronizer that performs a bunch of tasks, typically required to receive and decode a digital signal from the air. Don't you also want a throttle block after the file to emit samples is stable? Yes, I absolutely want a throttle block, because otherwise it will just read the file and send it like as fast as possible, and this is probably not what we want. So, but can we actually use this symbol sync thing if we only have a... Okay, we can do this. Okay, so let's read up on how this works. Or maybe I'll just go with the simple solution or like the basic solution, and then I'll do this at some other time and explain this. So samples per symbol. Yes, that's also an issue because we don't really know that. I think. You know what? Let's discard this for now. Let's just go the simple way. Let's make a Python script to do this. So the first thing we need is like a Python library to decode a wave file. Right. Is this even in the... Wait. Is that in the standard library? Wow. Python is amazing. So as I said, we need to open this wave file and decode it to get the actual audio data out of it. Luckily, in Python, there's a built-in library for this. So this will return this. Yeah. So we will open the, what was the file called? Yeah, sound.wave. And this should be in read-only mode, like this. And how does this work? Read objects. Read frames. Read this number of frames. Okay. So let's just try that. Try that it works. We'll just read one frame. So we'll just do this. Just see that everything works. Yeah. That's all good. So I guess the easiest way here would actually be to just read the whole thing. So can I do just get number of frames and then read that many frames? Num frames. Ask how many frames we have. Okay. Then we read that many frames and we do absolutely not print that. That would be a mess. But we can just... Oh, right. Was this a stereo? No. Mono, 44.1 kilohertz. Okay. But why? Oh, oh, yeah, of course. You get 16. But this doesn't make sense, though. If it's... if it's a 32-bit, okay, it is 16-bit audio. So every frame we have a 16-bit value, 2 bytes representing the amplitude of the wave. So we get this as a pair of bytes, but of course we want to parse this as a 16-bit integer. And are these, yeah, little endian. Okay, that's good. So what we do now is we need to parse this. So we need to take the sequence of bytes and convert these into a number of 16-bit values. And so this would be correct, I think. Yes. So what we're doing here is that we're using this struct unpack function to say that we want little endian encoded, or we want to decode little endian encoded numbers, and this many of them, and we want them to be signed 16-bit values. So you can read more about this format in the Python struct libraries. So this is a very, very nice library for like encoding and decoding numbers to bytes and vice versa. Super nice. So now we have a sequence of numbers. So we have, if we go back to the thing here, we have this like here, you can actually see the individual samples. So we have an array of these numbers in our Python script. So now we can actually start to decode this. And as you can see here, when you look at it like from afar, it looks like it's just like one value constant here. But of course, this is a sound wave, so you see the actual amplitude is just going up and down all the time. So we want to take, or one simple way to do this at least, is to take like a rolling average here. But of course, if you do that, like if you take an average over this, since this goes from like both the positive and negative, like if you take an average of this, it will be 0, because like the positive and the negative values will cancel out. So what we will do is we will take just the absolute value of this, because we're only really interested in like the amplitude and not the direction here. So if we take the absolute value first, we will flip all of these, like all of these curves going down, they will be just flipped, so they're going up here instead. And then we can start taking the average. So we can do, actually, let's do this. So we just go through all the values and take the absolute value. And then we can take this. I should actually plot this, but yeah, you will have to just imagine these things. So now we've transformed this wave going up and down into a wave that's going just on the positive side. And then we can start taking like, because we only need to differentiate between like, you know, signal or not signal here. So we can do a lot of like sloppy stuff and it will still work. This is not like super sophisticated signal processing stuff. So we will take this rolling average of, I don't know, 20 samples or so. Maybe that's good enough. Yeah, let's try that. So we can do that by, what's the easiest way to do this? Yeah, so data average, this would be we take the sum of a range Yeah, so there's a suggestion on Python generators. Yes. Yes, that's actually a very good idea, I guess. But wait, how would that? You know what? I'll just do this. So we'll just make this like average window size, like 20, or well, let's do this and just do this and then do this. So we take the sum of a range and we take the sum of this range going from like the current position minus 10 plus 10 and we divide by the number of points. Right, yes. So this suggestion about generators is actually very good. But I'm just going, fast and sloppy here for now. So this range of indices, we just want to start at 10 because we'll start at the this index because we can't subtract like beyond 0, and then we want to go on until the length of the data minus this window size minus 1. So if we run this again, and I don't make programming errors, for I in range. Okay. So now we've taken the average of a number of places. So now we should be able to just threshold this. But actually, let's see if we can print some values here. What's the... I want to get like the max value in this averaging thing, which is 2,786. And of course, the minimum should be 0. I really hope that's true. Yes. Okay. So now we have an array going from with numbers. Some of them are 0. Some of them are this 2,700, and then there will be some stuff in between. So we'll just, we don't really care about the value. We just need like a binary 1 or 0. So we just need like a cutoff. So let's just try 1,000 then. So for every value in this array, if the value is over the threshold, we produce a 1, otherwise a 0 for every value in this average thing. And now we should have a sequence of ones and zeros, but of course, for every kind of like, for every, what do you call it, like every logical one in the signal, like for every this, we will have a whole bunch of ones. So we kind of want to like reduce this to like a single bit, that's one, and so on. And this space here should be like 1 0, and this should be 1 0, and so on. So I guess this is where some plotting would just help us, or we could find like the shortest let's actually just plot this to start with, just see what we have. Matplotlib plot points. Yes, and right. So we use this matplotlib and numpy. We probably don't need, but whatever. So we can do this. And the x-axis is just the range of the length of these data bits, and the y-axis is the data bits themselves. And if we run this, and I don't have, you also actually need to call show on this to actually show the plot. Okay, this is something. Let's see if this is reasonable. We have here 4 pulses of what seems to be equal length. Like this looks pretty good. Let's look at this. We have 4 of these, and then like 2 shorts, and like a bit longer, and then shorts. We have, yeah. So this is kind of good. This is nice. So let's just see. So this is one of these shortest segments, and it seems like this is going from like 81,000 very high to like 84,000 something. So it kind of looks like this is like 2,000 samples long. So what we could do, we could just be super sloppy and just say that like 2,000 is good enough, and this signal is short enough that this is not going to drift too far. So if we just start at some specific offset and then just count, we'll just take 2,000 samples at a time, and we will be happy with that. And actually, since these things are aligned to something that is like divisible by 2, we can just start from the beginning, actually. So yeah, let's do that. So this means that we can just do kind of like the same thing that we did when doing the rolling average. But we'll do so for every we have like symbol size is 2000 samples. So we'll take the slice of like 2000 samples, and if this contains more ones than zeros, then we produce a 1, otherwise a 0, and we do this for actually we can do this instead with the range. We'll do the index plus symbol size, and then we do for I in range from 0 to the length of the data bits in increments of symbol size. And now if we print this, we have something that's very reasonable. You see here that we have 4 1s, 4 zeros, 4 1s, 4 zeros. And then we had this pattern that we saw. We had the 2 shorts, and then we had these like slightly longer, and so on. So this is probably the bits of the solution. So now we can just decode this into bytes. So first, well, this happens to actually be 8 bits, so whatever. So now we're just going to collect these into bytes. So we will take, yeah, we will do a really ugly thing here where we will we can take all the bits and just join them into a bit string, like an actual string. So like this is not, this is a bit of a dirty way of doing it. I'm having issues programming today. And then we could then take these and we take a slice of these data bits from I to I plus 8. We treat this as a binary number. So basically we're converting like all the bits to strings. We concatenating the strings, and we're taking slices of that and then parsing the string as a binary number. Like it's dirty, but it works. So in increments of 8. And let's see if this works. Yeah, so here you get the flag. And the flag is foreshadowing _ thinking emoji. So yeah, that took a little bit longer than I had hoped, but that's how you can do some basic signals processing in Python, and like plotting stuff, and looking in like Audacity and stuff. It works because the signal is so simple and there is so much room for error and so on here. So yeah, that's nice. I would like to try this kind of new radio solution at some point though, but that's for another day. And then you can do this very satisfying CTF feeling of closing 1,000 tabs. All right. Oh god, we have this challenge. Oh yes, the universal radio hacker. I've used this like once, and I was not great with it, but this is a pretty cool tool to work, like play around and work with these signals, and it has like a lot of tools and utilities and stuff for doing a lot of these basic things. And yeah, it's definitely something you should check out if you want to play around with the signals processing stuff. So time for the next challenge. This is gonna be horrible, actually. So, I mean, since I'm one of the organizers, I know most of the solutions to these challenges, and this one was something that people had issues with. So this was also one of the ones we presented during the end, the closing ceremony. And actually, I'm probably just going to present the reference solution here, because this is really fiddly. So we're given this image. So let's look at the image. And the image looks like this. You have a bunch of seemingly random pixels, and then there's this like diagram showing kind of like how colors relate to a 3D space. So what this is hinting at is that, a pixel is like a vector with 3 elements, like the amount of red, the amount of green, the amount of blue. But it could also be interpreted as a point in a 3-dimensional space. So the idea here is that you can take all of the pixels in this image and actually plot them in a 3D space. So I'm probably actually just gonna... No, wait. Yeah, let's start out on our own, and then we can actually just, because this requires a bit of filling. So we need to make some program a little bit for this. So we want to plot. Let's start with just plotting all of the points in a 3D plot, and then we can see what happens from there. So first we import an image from the pillow library, and we open, and we take the challenge file. And we also need like matplotlib, plot 3D points, maybe 3D scatter plot. That's this is what we want to do, I think. So okay, so we just need to extract all the points. So this, I think there's just like a get data. Hello image get data or something like that. Or there is like one function to just get like an array of from string, from buffer. Return the sequence of object containing, yes, that's the one we want. Get data. So let's just print like 3 of them just to see that. What? Can't we? Oh, you should do list. Okay. So let's do this. Okay, that's cool. So we just get a sequence of pixel values, and now we just need to extract them. We need to like transpose this to get like one list of X, one list of Y, one list of Z. And there's probably better ways to do this, but this is a quick way to do it. So do this, and then we can get this plot thing going, and then we need to call show on this, right? Yes. So this should give us, well, you also need to actually import stuff. Unknown projection 3D. What? Do I need some? Okay, they do this in a different way. Maybe this is changed. Okay, wait. Okay. Yeah. This looks horrible, and the frame rate is also horrible. Because there's a lot of points in here. Maybe I should do some like filtering or something. But actually, yeah, we need to do something to... Yeah, I mean, you can see that there's something going on. Like, there seems to be, you know, some kind of diagonals or something going on in here. So there's definitely, I mean, they're not... Like here, you can see these lines like this. Like here's something, here's something, here's something. So it's not just like a random distribution. So there's something, but we need to do something to be able to do this. Like with more than so, and here you can definitely see these like lines. Oh, maybe if I can just turn very slowly here. Yeah, so I probably need to do something to be able to... But it kind of looks like things are like converging to some kind of point here. I mean, look at this, for example. I wonder if I can... This makes sense. Yeah, so basically it kind of looks like, you know, things are like pointing to a point here somewhere. And it turns out, because I'm just gonna skip ahead to this step. Like if we look at the reference solution for this, they use... Oh, wait, can I even run this? So they also do the same thing. They plot this image, and then they specifically put the camera in a specific position with a specific field of view. Oh, will this not work? I mean, obviously, that's not the one. Like, was there an update to this? Or... let's try to just check this one first. Of course, this should not be absolute path. Okay, now the question is, can I install this? I heard that some people had some troubles with this package, but we'll see. Oh. Okay, so this is a much better program for doing what we want to do. And it's actually kind of good because it was in the wrong position, so we actually have to figure it out ourselves. But you can now clearly see that, like, you know, this is definitely not like random. Can I... You can see like at the bottom left here, there's an R, there's an O, is that U, N, D. So it seems like it says round here. Oh, look here. You can see the S, M, maybe with some wishful thinking, and like the curly bracket. So you see that there's like definitely something going on. Oh, and this now it's starting to look better. Maybe we could... Yeah, now you can clearly see the SP up here. And maybe a 1 and an N. So it's like spin me right round. So that's that is the flag. Spin me right round, and then you have the curly bracket there, at the end. So yeah, that's how you solve that one. So plot them in a 3D space, get the tool where you can actually like manipulate them with like a smooth frame rate, jiggle it around, find the right position to look from, and you'll see the flag. It's quite a cool concept, I think. So so the final forensics challenge is this crushed picture. Yeah, I've never seen this video before, but yeah, it looked nice. Could be probably useful for a bunch of like visualization things. Visualization. So anyway, let's move on to the last forensics challenge. So again, we have this like crushed.png. By the way, also let me know if like, you know, I should enlarge the text, or, you know, if there's like anything unclear on what's going on the screen. But yes, what did we say? What did we say? Okay, so let's look at this file. It says that it's a PNG image, but it's a 0x0 PNG image, and that doesn't make sense. Like, you typically have positive dimensions. So what happens if we try to open this? Yeah, fatal error reading PNG image file, invalid header data. So the image is somehow corrupt. So let's open it in this hex editor again that I like. So again, we have this file. It manages to like parse the structure of it. You can see first it starts with the PNG signature, and then, for example, here you have this header thing, which it claimed was corrupt. We can expand this. We can see that here is a... So the way PNG files work is they consist... So first they have this the first few bytes, but then they have a sequence of chunks, and every chunk first has a 32-bit length value, and then a 32-bit type. It says which kind of chunk is this. So this is an header chunk, and then you have the actual data of the chunk, and then finally you have a CRC checksum for the chunk. So and then different chunks means different things. So you have the header thing, and then you can have like color profiles, and then you have the IDAT, which is the actual pixel data. So we can see here that in this in the data of this header chunk, we see that the width and the height of this image, they both have been set to 0. So that's the issue here. We need to figure out, you know, what's the dimensions of the picture. So the way PNG files are encoded is that you take, or rather the way you decode them. Let's start from that end. You take all the contents of these IDAT chunks, you combine them, you clib decompress this, so they are it's compressed data, so you decompress the data, and what you end up with is sequences of lines. So every line starts with one single byte, which explains how that line is encoded. And then you have a sequence of pixels, which the size of them will depend on the color format, like if it's like a monochrome or RGB or RGBA, and so on. So, but for example, in the regular RGB, you would have 3 bytes, the red, the green, and the blue. Or depending on the encoding format, it could also just determine the delta from other directions and so on. But it's not really important. The important thing is that you will have 3 bytes per pixel if it's an RGB thing. So for every let's pick out the or like bring up the editor. So let's say the picture is W pixels wide and H pixels high. Then and we have an RGB pictures with like 3 bytes per pixel. That means that every line will have 1 byte in the beginning plus 3 bytes times the width of the image. And then there will be one such sequence for every line times the height of the image. So the length of the total image data will be this value. So what we can do is, if we just take the image data and we decompress it so we get the full length of it, and then we kind of find the possible solutions to this equation. So we can just factor the length, and then we will see a bunch of different combinations that we could have here. There's also a way to kind of like brute force this in a sense visually, and I will show that as well. But let's solve this challenge. So we need to extract the pixel data. From the file. And we can just actually very quickly write a super small PNG file format parser. This is extremely simple to do. So what we do is that first we just read the first 8 bytes here. We will do a very, very sloppy parser, which like disregards most of the data. So we read 8 bytes, we skip them, and then we start reading chunks. So for every chunk, we need to fetch the length of the chunk. Which is 4 bytes that we treat as a 32-bit integer. So we do this like while true. Chunk length. And then the chunk type is the next 4 bytes. And then the chunk data is... oh, actually, I should be very careful here. The length is actually a big endian here in PNG. So this is a mistake. It should be like this, big endian format. And we then read that much data. So we read these 4 bytes, the length. We read the type, and then we read the data. And that's the chunk data, and then you have the chunk CRC, which is another 4 bytes. So we do this. If the type is IDAT, then we add this data to the... We basically concatenate all the IDAT headers. And finally, if the chunk is of type IEND, we stop. So then we have all this IDAT data. So we call this like pixel data. And we just print the length of the pixel data. We run this, and I need to add, because struct unpack actually returns like a tuple with the values, but this is a bit like inconvenient when you're just getting one value. You still have to like do a index 0. Whoa, what did I? Oh, I wanted to print the length of the pixel data. So this is the length of the data in the file. So let's just factor this this number. So here you have the different factors. So, I mean, now we get a couple of different possible combinations here. Where we have this equation. So it means that we should like divide these, we should group these factors into two halves, and one side of them should be one more than a multiple of 3. And luckily there aren't that many combinations. So we can use a very nice Python library, the iter tools, to get I think you can do this. We want all different we want like all the subsets of this list, basically. Python combinations is the one we're looking for, right? Or well, yeah, so we can just do combinations and then of increasing lengths. So so we have the factors, which are 2, 2, 3, 5, 4, 3, and 409. And then for subset length, so for each possible, like first we try all the variants where we only have one element, and then like all the combinations of 2 elements, and so on. So we call this like height factors, and tools. Oh, we should actually import this. Combinations, and then pick from factors, and we pick this length. So we can just do this, and can only this should be outside. Okay, so these are all like the possible factors of the height, and then we say that this is like the candidate height, and we just multiply these together, So this is like the different possible heights of the image. And then we check if we take the length of the pixel data and we divide this by this candidate height, and then we subtract 1 from this, and then we try to divide this by 3. And if the total length divided by the possible height minus 1 is divisible by 3, then this is a consistent height. Like that could work. And then that would mean that actually we should save this and call this the candidate width. So we do this and we get these possible, maybe I should add a space. So these are the possible dimensions of this picture, it seems. So we could just, and like from these, some of these look more reasonable. Like probably these are the most reasonable choices. So actually, let's just try to edit this file and wait, which one did I put? Yeah. And insert these values and like see if that works. So actually, let's just save as fixed. Right. There is the CRC. So there's a question if I've done anything more than forensics. No, I'm just finishing up the forensics. So we'll probably have to move a little bit faster unless I'm gonna be sitting here all day. But yeah. Yes, you probably have to fix up the CRC and so on here. Which you can do. But let's just show the other, like, less sophisticated solution, which is we just take the decompressed pixel data and we write it to a file. And then we open GIMP and we open file. We do show all files and do not select type automatically. We pick the dat file. We go to raw image data. We open this. We make the window a little bit larger. And here you can try to interpret the data as different dimensions. And this looks very much, you know, let's look at the logo of the competition. It looks very much like the logo of the competition. So first of all, let me actually close down few things here. And this one we can also close. This one. Okay, so yes. Here we have, and now the reason this works is that, as I said, like the pixel data is just this sequence of bytes, so we can just basically read them as is. The reason it looks a bit strange is because you have that for every line, you have that extra byte, which is used for deciding like the type of encoding used for that line. So this means that like you will be off by one for every line of the image data that you read. You will get off by one, but it's good enough for like getting the general like gist of the contents of the image. So here we have the result, and let's see, is this width value somewhat close to any of the things? No. So maybe I did some kind of mistake when I tried doing this. Oh, I know what mistake I did. I didn't here, of course, it shouldn't be divisible. Like this equation here is no. Okay, whatever. I made some mistake in my calculations there. But basically, you get this, and you get the flag. Size does sometimes matter. And we can verify this is the flag. Great. So this load the raw image data tool in GIMP is sometimes quite useful, and sometimes you can like use it directly on things that are not like memory dumps and stuff. If you believe there's like an image in the memory dump, and so it doesn't actually need to be just an image file. So let's do this. So what category do we do next? Good question. Let's do some reversing, I'd say. By the way, you can factor numbers like that on the command line. Oh, you can. What tool do I use for factoring that directly in the command line? Is there just a... Oh. Right. Nice. I didn't know about that. Thanks. Okay, so there's a request for pwn. Yeah, okay, let's do pwn. Let's do pwn. So let's close down some tabs. Let's close down this. And so we switch over to pwn. So the easiest one here is this. This is basically the technical Swedish translation of buffer overflow, and like no one ever uses this term, but it exists. Any weird FPGA challenges? Well, there is a Verilog challenge, but it's not weird, and it's very simple in the reversing category. I mean, this is a beginner CTF, so you know we didn't want to go crazy. I think we already made it a little bit too difficult. We should probably tune down the difficulty a little bit for next year. Yeah. I mean, we wanted to do like a big mix of things, but we'll get to the Verilog, which I also realized during the competition that like the Verilog doesn't actually run properly on an FPGA. I made some kind of mistake. You can still solve the challenge, but it's not actually working code. But we'll get to that. So the phonable challenges. So the first one, the first buffer overflow challenges. Have you heard about the new bug type, buffer overflow? So, I mean, yes, we have, but okay. So what do we get? One thing we get is a remote service. So I'll just go ahead and start the remote service while we're working, and we get this file, which is one of these ELF binaries. We can try to run it. It says, how much do you want to write? We want to write 10. And yeah, and then it exits. So yes, the stream recordings will be available afterwards on the channel here. There's probably going to be like some kind of time window where it will not be because like YouTube is processing and stuff, but yes, it will be. So yeah, I'm just thinking about now for all these pwnable challenges. I mean, I would like to use IDA because that's like my tool of choice. On the other hand, I guess it would be more reasonable to use Ghidra to show what you can do with a free tool. Yeah, I should probably use Ghidra. Luckily, the challenges are super easy because I'm not good at all with Ghidra. So I'll just show. So basically, what we're going to do here. So we have this ELF binary, and also we have this server which is running the same program. So we need to find a bug in this program and exploit it. So there's a question if IDA free is too limited. Yeah, I think actually it's probably just easier to go with Ghidra actually than IDA free. And I think for most of these challenges we will be just fine with just Ghidra, even though I'm not very good at it, and I'm not a huge fan. But it's free, so it's very accessible for beginners. So basically, we're gonna look for some kind of bug in this program. So we're gonna craft some kind of input which will allow us to exploit the program. So for that, we need to do some reverse engineering of the program, and for that you need some kind of tool to do this. And one tool that's pretty good and freely available is Ghidra, released by the NSA. It was like a year or two ago. So you can download it and use it completely for free. And if you run it, something like this will happen. Let's just remove this. Was when I showed it during like the Q&A session. Let's do close project and do new project, and yeah, like the Ghidra UI is absolute garbage. But you know, you can't. It's difficult to beat the price. So the project. We'll call this solution stream. So we'll create the project. So yeah, I mean, like, it's like, don't get me wrong, it's really great that there is a tool like this for free. That, I mean, it is very powerful, like, if you know it. But yeah, there's also a lot of stuff that's maybe not that great. But like, you can use it for a lot of things, and there are definitely like strong sides to it, and it's free. So it's definitely, like, for beginners, this is absolutely perfect. So yeah. So this is, we have a created a project. We have opened the code browser module, and we will import a file. And let me just double check that we are in the right place. Yes, so we will import this buffer overflow binary, and we'll just use all the default options for like analysis. So like, yes, please analyze all the default stuff. Okay. Yeah, I mean, of course, like, it's great to have a free decompiler. It's just, I'm way more used to using IDA. Yeah, so the idea of project is also great. For example, sometimes in IDA, I kind of wish that you could do that if you have if you're, say, you're reversing some like server client thing, and you have a bunch of you define structures and stuff, and it would be nice to be able to just easily share them between binaries and stuff. So in that sense, like, the project thing is also good, but it's a little bit annoying that you can't just like do like an ad hoc analysis, just open a file. Yeah. So anyway, we have some symbols here. We have functions, and in this program we have first some just general like libc related stuff, but we also have a main function. So here you will see the disassembly of this function. Yes, there's always, yeah, you have a stuff project, definitely. And then here you have the decompiled version of the same code. So this is roughly equivalent of what the original source code looks like. Sorry, I clicked menu. I meant to click main. This is the main function. So here's the disassembly, and here is the decompilation. So first there's some call here to disable buffering, so just to make our lives easier. And then they would call the menu function, and then we would call the hacks function. So the menu function just prints some data. It's probably this how much do you want to write string. And then we have the hacks function. Okay, I was wrong. Here they print like how much do you want to write, and then they call this read int, and then they call read with the value of that. And they read this into this buffer here in the stack. And you see there's no bounds checking here. So we have just a straight up classic buffer overflow attack where we can overflow the buffer on the stack. So now we have to before we move on here, we need to look at like what protections and stuff does this binary have, because that will affect our strategy. So we can use a program called a checksec, and this will tell us that there is no stack canary. That's also something we can find out ourselves by just looking at the code here and see that there is no there's no stack canary operations being performed here. And another thing is that this is not a position independent executable, which means that this thing will always be loaded into the same location in memory. So this is good. This means that we can just overflow the stack buffer and overwrite the return address and jump to wherever we want. And in this case, there is a print flag function, but this is not called from anywhere, but we can call it ourselves. So in this stream, generally, actually, throughout these Pwn challenges, I will not go like super deep into exactly how these mechanisms work. I can instead recommend that you check out on my channel. I have here a recorded lecture from when I was lecturing at my university and talking about like the basics of binary exploitation. So if you watch this video, you will I will go through all of like these basic concepts about like buffer overflows and like overwriting return address, return oriented programming, and so on. So I will just talk about these things very briefly throughout the stream now, and then you can like reference this lecture that I've recorded. But also like feel free to ask questions in the chat and so on about specifics as we go along. So let me just yes, so the idea here is that on the stack there will be the buffer, there will be some other stuff, and then there will be the return address. And we will just keep writing stuff until we overwrite the return address, and then we will jump to the print flag function. And to make this easier, we will use the Python Pwn tools framework. That's also something I really encourage you to use when doing these kinds of things. It's like a really nice Python framework for doing these things. So what we will do is we will load this binary and we will start it, and I can just drop into an interactive shell. So I'll just show what that looks like. So so now we can just interact with the program normally, but we want to automate this. And what we also want to do, I should bring this up a bit to not have my camera cover this. So okay, so what we want to do now is we want to wait for this prompt. And then we want to send, let's say, I don't know. We know that the buffer could hold like 264 bytes. So let's send like 512 bytes or something. Like we don't really know exactly the offset yet. But let's do that. And then we actually create our payload, and we will use, okay, first something. Just set up the context to say that we are doing a 64-bit thing. So we will generate a specific pattern with this cyclic function. I can actually just print this. Just show you what this looks like. So we generate this pattern, and the nice thing with this. Oh yeah, so this is not. So there's a question if this is 32-bit. No, so it's 64-bit. We did all the ponables for this competition in 64-bit. But yes, it's definitely, you know, you should look at this with using file. So I mean, it could be 32-bit, could be 64-bit, but in this competition we did everything 64-bit. 32-bit is like, I mean, it's good, still good for teaching the basics, and I still do that, but it's getting a bit old at this, like nowadays. At least on like x86, like Linux or Windows environments like this. Of course, in like embedded devices and so on, you can still have architectures with like 16-bit and 32-bit and so on. But anyway, the cyclic function, it will generate this pattern, which is really nice because if you take any subset of, any string of length 8 from this string, you can immediately calculate the offset in the string. So, and I will show how that's useful, because we are sending all of this stuff, and somewhere, like some of these bytes will overwrite the return address, but we don't really know if it's here or here or here. And of course, we could just like hedge our bets by just like putting the value we want everywhere. But that's a bit like unsophisticated and probably won't work in more complicated setups. So let's be a little bit more specific here. So we send this to, yes, exactly, for any substring of 8 characters, you can identify it. Of course, if it's shorter than that, if it's just like 2 A's, of course you don't know where in the string that it's located. So we send this and we check what causes the crash, and then we can use this to determine, you know, exactly where we should put the return address that we want. So let's stop printing this, and before we send this, we pause this. So now the script is paused just before it's about to send this. So we use GDB. Actually, let me increase the font size. And we attach to this running process. Let's see. Now I thought I had fixed that. Sorry, one moment. I've been playing around with like I've been playing around with my debug setup. So you use GDB attach from Pontus. Yeah, but like I wanted the layout as I wanted it, but why is this? Let's just comment this out for a moment. Where is it reading these settings from? So there is integration for this, so I can actually. But the problem is that I haven't really. I had a really nice setup where I would actually do. So I can show you what I was working on. So let's start Tmux, and then I had this, and then in the script, let's change it from this to
what's it called? Pwn tools, GDB, debug. So can't I do this with... Can't I do this? No, I'll have to. Right, so there is a Tmux integration in Pwn tools and GDB, but and the thing I wanted to do was there's also just built in. You don't need to actually add any commands or anything. It's just the default behavior in Pwn tools. Like if you do GDB debug and in Tmux, it will do this split. But I added a small extra touch to this, which I thought was really nice. Although let me just stop this to... So this, why can I? Oh shit, yeah, it's the... So what you can do is you can set the, you can set the context thing to redirect to another TTY. So you can get a very nice layout. How do I copy stuff? So I'm very new to using Tmux in the first place. But what I wanted to do... Oh no. Now something's really... What's going on here? Why is... Okay, something is really... Something really messed up in my terminal. So what I wanted to do was to do this, and then run this, and then do this and this. So now you have this split where I have the exploit script running here. I can input my GDB commands here, but I will get like a full half screen of output instead of the... Because I don't want... If you do the default split with like GDB, and you will get half a screen with the exploit script, and then half a screen with GDB, and then half of that with like it's complete wasteful use of this screen real estate. So because typically we only need like a little bit of output from the exploit script, and we just need a little bit of space to like input our commands and so on, and we want like a large area to view data. So this is like the thing I've been working on, but it's not, as you see, like it's not fully, like it's not super convenient yet to say. But I had this function, and so the usually it would work with the default values. The problem now is like I have this
pane down here running the Docker thing, and yeah. So I need to like work on like how to just do this in like one command or something. But this is my new fresh setup for debugging. So let me explain so this was like a little bit of a tangent for people who have done this a little bit before, but what we have now is wait, why didn't right. So what I'm using here, as I said, in Python, we're using Pwn Tools. And Pwn Tools is starting GDB, the debugger. And it has this integration with Tmux to just split off GDB in another pane. And then in GDB, I'm using an extension called Jeff, which is very nice. So GDB Jeff. It adds a lot of these like nice different commands and this like nice colors and interpretation of data and so on and so on. And I use the built-in feature of Jeff to have like a separate Tmux pane where I print the output of the debugger. So that's nice because you get more screen real estate to like view stuff than if I would just do it in this like half thing. And typically you want more space on the like on the vertical dimension. Like it's not super useful to have a super wide debugger output typically. So anyway, with all of that out of the way, we can just let the debugger continue, and then we the exploit script is still paused, and we let it continue, and we see that we get a segmentation fault, and here when it's supposed to execute the return instruction, it crashes, and this is the top was that how you did it? Okay, right. So at the top of the stack now we have this string. So we can go back to our exploit and say that the length of this padding is, so we use this cyclic no, not cyclic length, it's called cyclic find is the function. So this will, and just print that and then we can run this, and it will say 280. So the return address should be 280 bytes from the start of the payload. So our payload will consist of just that many bytes of whatever. And then we want to pick the location of this print flag function. So one way we could do this is we could go to Ghidra, and we could see that this is the address of that function. We could copy that value into our exploit script. But we can also just use Pwn Tools directly to look in the symbols table of the binary and take the address. Now, this will return a number. So we need to pack this, since this is 64-bit, we need to pack this into a 64-bit like 8-byte sequence that represents the address. And that's our payload that we will send. And now, just to make this work locally, because we'll see that the print flag function calls a tries to open a flag called flag.txt, and we don't have such a flag, so we will create a flag file and just have this like fake flag in there to be able to try this locally. And then we also leave it running interactively at the end so we can see the output nicely. So let's try this again. Go back to the terminal. We run this. Continue. And it's paused. So now we'll press a key and we'll send the payload. And then you can see here that it prints the flag. So it seems like we have a working exploit. And now we need to try this against the remote server. So instead of attaching a debugger and running the process locally, we will connect to a server. And like in a real competition, of course, this wouldn't be localhost. It would be the remote server, but we're just hosting it locally, and we should be able to run this, and we get the real flag out of this. So that's how you solve that challenge. So basically, for pwning, watch my lecture, get pwn tools, get GDB, get Jeff, and get Ghidra. All nice free tools that will make all of this much easier. Right, so what I'm gonna do here is actually to temporarily skip this one, because this is kind of a different flavor of challenge. So we'll go directly to this printf in a loop. So let's just move this aside a little bit. Yeah, so this comment here, like stack exploitation is okay, heap exploitation is another thing. Yeah, definitely it gets a bit trickier when it comes to heap stuff, and then yeah, I'm not very good at that either. And then you have like kernel stuff, which is also kind of like a bit of a different category, and a kind of more like application of this. You can see things like browser exploitation has its own like language and like things they do and so on. And it's starting to pop up more and more in competitions. We played a CTF recently where we had to write an exploit for Chrome. It was actually kind of a fun challenge because it was a real bug that had been patched, but there was no publicly available exploit for it, I think. So yeah, it was pretty cool. Some of my, I didn't work on a challenge, but some of my teammates solved it, so that was cool. But anyway, that's more advanced stuff, and we'll stick to the basics for now. So, printf in a loop. We get this file. We have a container. I'm stopping the other container. So, heard about shell codes. Is that like question or a statement. Yeah, so shellcode is kind of dead. Yes, I mean, in some cases, I guess it can be used for not like the initial step, but as kind of like a finishing step. Like you do some other exploitations, some like ROP or whatever, and then you manage to call like a map or something to create like an executable and writable region, and then write some code into there to just simplify the exploitation and so on. But it's not really an important concept in most contexts anymore. So let's start the container as well while we start working. Oh. And again, we have a 64-bit ELF binary. So let's go to Ghidra and do close this one, save, yes, like import file, and go to Printf in a loop. Like the name kind of, you know, suggests what's going on. So this thing, like the 90s must have been wild, no binary protections, whatever. Like, yes, but also the tools were much worse. So like pros and cons. And the availability of information was also much lower. Like you couldn't just go to like read like a very detailed article about exploitation techniques like aimed for beginners, or like watch a presentation or YouTube or whatever. Like it was the like fewer people knew about things, and the information was not shared as broadly. So yeah, that's also probably much more difficult to get into. Like this is also, I mean, way before. Like I didn't really get into IT security until like 2013 maybe. So again, we have the main function, and what is it doing? It will turn off some buffering like the previous one. We don't care. Here, I think this is stack cookie stuff going on here. And basically what happens, it reads some input, and then it gives that input to printf. Yeah, so this is a classic example. I really, the white chat text on the white background doesn't look very good. I should add like a black outline to the text or something there. But anyway, this is a classic example of a format string vulnerability, something which I also cover in a little bit in this presentation. But the basic idea of it is that in a normal situation, if you call printf, you would have some format string and some variables, and you can have a variable number of arguments to this function. And the function, the printf function, doesn't know how many arguments you passed to it. It just assumes that there will be enough arguments to fill all the placeholders in the format string. So if there are 2 placeholders in the format string, it will just assume that there are 2 arguments available. and the arguments will be pushed on the stack. So if there isn't an argument there, it will just read whatever is on the stack in the corresponding position. So if we run this program, first of all, let's just run checksec, although this will probably not be very relevant at all. In our case, it's not position independent, although this will not really matter, but it will maybe make the exploit a little bit faster. So if we run this program, it seems that it does nothing. We input some data, it prints it back. But if we put in like a placeholder like this, we get values back. And if we input multiple of them, we get multiple values back. So we are leaking data from the stack. So we can use %x or %d to leak stuff directly on the stack, or you can use %s to interpret something on the stack as a pointer and then leak whatever it's pointing to. And none of that is very surprising if you programmed and used the printf function. Like, that's, you know, common use cases. But what's more surprising to most people is the %n placeholder, which will allow us to write data. And what this thing does is that the printf maintains a counter on the number of characters it has printed so far. There's a comment, Pontus has a fully automated format string exploitation. Yes, which works decently. In this case, it absolutely works because this is such a trivial case. But it's good. Like, you should understand what's actually going on, because it's definitely not always the case that the PwnTools module will work. So the %n placeholder, what it will do is, so printf maintains this counter of how many characters it has printed so far. %n means that it will take the corresponding argument and treat this as a pointer to an integer, and then we'll write the value of this counter to that integer, and then continue parsing. And this means that we can also write data with printf if we control the format string. And the reason, like, the point of this feature is to be able to do aligned, if you do like print multiple lines, like you want to print like a table or something in ASCII or so on, you can like print the first line and you can store like how wide did that column become, and then you can use that in the next line to decide how much padding you need and so on. So that's the intended use of the %n feature. But yes, so we can now exploit this by let's check again here. We had we can leak data, we can write data, we have no pi, so everything is in a fixed place in memory, and there is a print flag function. So the only thing we need to do is to override some suitable pointer with this print flag thing. And so we basically just need to figure out like what thing we need to overwrite and with what. So one thing you could do, yes. So we could either try to like overwrite the return address on the stack. The problem is that the this main function never really returns. So that's going to be an issue. Another thing that we can do is that since this is a dynamically linked program, we could just, what that means is that all of these like library functions, they are of course in a separate library in libc, and what we have inside this binary instead is just a table of pointers to these functions. So we could just overwrite one of those pointers, and the next time that function is called, another function is called instead. So, for example, if we overwrite the pointer to the fgets function, the next time you try to call fgets, we will jump somewhere else instead. And I'm just now trying to interpret, because I have never, this is, yes. So what you will have in the program, you will have two things. You will have this small trampoline function, fgets. And the only thing this does is that it looks up this value in this table and it jumps to that location. So this is not the place we want to overwrite. This is the code that makes the lookup in the table. We want to overwrite this, the entry in the table here. So this is the address we want to, these 8 bytes we want to overwrite with the address of the print flag function. So that's one way we can solve this challenge. So let's close this and then write a new script. So we can do something like this. Run the program, great. Yeah. So what we need to do now is, yes, there's a print flag function. Yeah, I mean, for many of these challenges, you can try to get the shell instead, but you know, why make it more difficult when you can just do it the simple way? Or so this is the Pwn tools format string exploitation thing, and we could probably do this. This is probably just straight up this automated, yes. So let's try this. actually. So what we need to do is we need to create a function which is like the interface to the program. So in this case, it's super simple. We just send the string, we get back a result. In other contexts, this might be more complicated depending on how the format string works. Maybe it's like you have to go through like a menu thing and set the name of an object in one place and then navigate to another place in the menu to actually print the thing. So then you would program all of that logic into this function. So this is like the interface that you have to implement for the format string module to work. So it needs a function that takes a payload, sends it, and returns the result of that printf call. And then we use that to create this format string object, and we pass this function as an argument. And then what do we want to write? We want to write, we have the address, like where we want to write things is the, this fgets value in this so-called global offset table. If I'm not mixing up the names. And so this should be something like this, but I don't think that's how Phone Tools writes it. But that's where we want to write it. And the what we want to write is the address of the print flag function. Actually, what we should do instead is we should use this one to just generate the payload first, so you can see what it would look like. Is it PLT? Yeah. I'm always mixing up like the GOT and the PLT. But yeah, possibly. I'm just wondering if that's the name that if that's the syntax that Phone Tools uses. So let me just do this. And all right, it's just dot like this. Okay. So it would be this. But we should actually not send it all yet. We should do this and just generate the payload first to see what it looks like, so that we can show how this would work. Wait, what's the 5 thing here? Offset. The first format is offset you control. Yes, this is something we will have to figure out. But anyway, I can print this and just, it will. GOT.printf also works. Yes, of course, you could choose either the fgets function or the printf function. But of course I mixed up the order. That was the issue though. Yes, no, 5 is not the number of words. This is the stuff already written. The 5 is like which argument is the first one we control. So this is what the payload would look like. And I can basically try to decipher this a bit. So what we're doing here is that let me just check. Yeah, so these C characters here, we are basically just using one argument as like a dummy argument, and we're padding it out to this many characters. So if you would run this, you would get an output of 246 characters. So this means that the internal counter of the number of characters written will be set to 246. And then we use this dollar offset thing to pick an argument that's not necessarily like the next argument. We can jump around and use different arguments with the like $ addressing. So then we will use this an offset here, or sorry, we'll use an argument as a pointer and write 256 to that location. So this is pointing to some of this data here, which will be interpreted as pointers. So this will write some data, and then we will write another 27 characters. So the counter of how many characters we have printed will be 246 plus 27. And then we look at the next offset, and here we use n, but with the age modifier, which means that we will write only a single byte. So this means that this counter here will wrap around, or like the least significant byte of it will wrap around. So we will write a fairly low value to the address defined by the next pointer argument here. And then we do this again. We print some more characters to increase the counter. We take the next piece of data here, interpret it as a pointer, and we write another byte to that location. And yes, I think that's it, basically. Those were all the only bytes we had to write, because by doing this LLN here, we will also set a whole bunch of bytes to 0 as well. So this is the whole payload, basically. And what we need to do now is, so this value here defines these offsets. So like the number, like which arguments are we actually controlling? So let's see if we would write an input that looks like something like this, and then we would do like %x, %x, %x. So this means that you get the output here. So this one corresponds to the first argument, this one to the second, this one to the third, and so on. So the question is, which is the first argument that contains data that we control? Yes. I mean, I know Pro Tools has automated function for this, but I'm just explaining. So this is what we will do down here, but I'm just explaining how this works if you're not able to use this fully automated thing. So you need to figure out what's the first argument you control, so that these $ addressing offsets are adjusted correctly. So it might be the case that like the stack layout is slightly different, or there's other stuff on the stack, or there are other arguments that you don't control, or whatever. So this is just saying that here, like you can see 1, 2, 3, 4, 5, 6. This is the sixth argument is the first argument that controls data, or that contains data that we control. So I don't know if it's 0 indexed. So if it's 0 indexed, it should be 5, like they did here. And this means that this would be the correct way to generate this payload. So we could actually try this. Again, we need to create a fake flag file. And we send this payload. So this is the generated payload. We don't use this this automated system. We just use these helper functions to generate the payload and run this. And it didn't work. So is this supposed to be? Yes, okay, so it was not 0 indexed. So that was like one way to do it. Or, as said, we could skip the manual thing and do the fully automated thing. So that means we just need to implement this function correctly, and then we create this object and we say we want to perform this right, and then please execute this and go. So this should also be able to do this fully automated. All right, I messed up the order there. Oh, yes. Right, so this also works. So now you see here that the function that we use is called 6 times to find the offset, and then once to perform the exploitation. So this means that the fully automated way to do this required 7 calls to printf. But when we did it manually, we only needed a single call to printf. So there might be situations where the fully automated one will not work because maybe you have a limited number of calls. There could also be cases where you have a limited number of bytes that you can send, so you need to optimize your payloads. There could be situations where you can use some kind of external knowledge about, maybe you know that one of the bytes you're writing to already has the correct value, so you can skip that and optimize your payloads and so on. So in some cases the automated thing works, sometimes it doesn't, and you need to be able to understand what's going on to be able to do this properly. But of course, we also need to exploit this against the server. And this didn't work. Is the server running? Yes. So this is not working for some reason. Why? Actually, we can do this. All right, okay. So it was working. It was just that the Yeah, so the flag was being swallowed by the exploitation step, and then exiting. So yeah, here you have the flag.
Okay.
Great. Actually, let's get rid of this. So that's that. Then we have the Brainfuck 2. Question, can we do some RE now? Yeah, well, let's see. Oh, wow. We've been going on for... No, I'll finish up the pawning, but and then we'll move over to the reversing. But or should we mix it up? What do you think? Have some more opinions? We could mix it up, actually. Let's do some reversing. Just need to remember what I've actually done. So just give me a second. So we did forensics, all of them, and then pwn. We did this one and this one, and then let's do some reversing. Okay. So we have the first reversing challenge, the Doors of Durin. So there's a bit of I made like a trilogy of reversing challenges here. There's the Doors of Durin, the Isengård, and Barad-Dur. And they are kind of like related to each other. And then there's these other two. And here you have the Verilog challenge that we will go through as well. And then some AVR reversing as well. So we'll have a good time. But I'll do these three together because they are related, and then we'll take these two. So Doors of Durin. What do we have? We get the speak friend and enter binary. So what is this file? Okay. We are supposed to speak friend and enter, and we try to do that, and nothing happens. Okay, so how do we do this? What is this? It's a file. It's an ELF binary, and yeah, what you can do is you can run strings on it to see if there's some interesting data. And here is something that looks like a flag. So could it be this simple? Yes. So the first reversing challenge is just like you like inspect the binary to see what strings it contains, and it seems like there was some interesting data in this. You could of course also, let's do this, open this in Ghidra, and go to the main function. And you can see here that it just does a string compare on the input against this value. So that's great. And then we have the Isengård challenge. And here, yeah, we're also only given the this binary, Saruman. What do you want, Gandalf Graham? We write something, and he says, "Save your pit in your mercy. I have no use for it." Okay. So what do we do here? We try to run strings. Seem to be a YouTube link, and then just other things here, but no flag. Okay, so we need to do better. Let's open it in Ghidra to see what this program is doing. And go to the main function. And what happens here? It asks for some input, and it just checks. It replaces if the input ends with a new line, it just removes the new line and like it replaces it with a null byte. And then here there is something going on with the input. Like there's something about like the index and then multiply by 2, and then you take like the input. Yeah, so it's like manipulating the input somehow. And here it's also doing something where it's like XORing the input, and eventually here it makes it does a mem compare against this target, and if that succeeds, it prints this. So we want to reach this. So basically what we can do is we can look at this target, and we can try to like invert these operations and basically calculate what the input should be. So let's do this by copying this stuff. We just copy this here to have as a reference while we reverse this function in Python. So what's going on here? If you look at like this and this, it's just a it's just a for loop. So it's like I just brute forced ASCII for that one using that code. Yeah, so this is actually another way we could do it. You could, since we can kind of see here that if we kind of look at the data dependencies here, like what values will affect what values and so on. we can see here that there's just like one small thing that you might miss that's important here is that if we look at how these things are defined, so the input array, we'll copy these two actually, because this is actually relevant. So the input array is an array of bytes, but the input 2 is a 16-bit, a pointer to 16-bit values. So you can see here that they assign oh, welcome Nishant. So you can see that we have, and welcome Ismail. We have this 16-bit pointer, so they assign the input pointer to this pointer, and then they make increments of 1 to this pointer. But this will then actually operate on 2 bytes at a time of the input. So that's just one thing you need to keep in mind. Oh, now there's just like a whole bunch of subscribers dropping in. Oh, sorry, font is too small. Yes, let's increase it. Is it? Please tell me if this is better. So we have, basically we could try to like make our understand, like make sure that we understand this code by just like implementing it in Python. So the input, we can't call it, I don't want to call it input because that's a Python function, so it will be input 1. So maybe I need to turn off the subscribe notification if this keeps, I mean, it's super nice that that there's a lot of subscribers, but yeah, maybe the sound is a bit annoying. So I don't know if you saw, but like we had this April Fool's thing on Live Overflow's channel yesterday, so maybe there's like a lot of people dropping in from there. So what we need to do is that we have this input, which is a byte array of like something. It's like, say, 100 characters, whatever. So what's happening here is that for we loop over the input, and then we say that the input, actually let's call this the exact same thing that's in the code. We say that we take the index plus 1 and we multiply this by 2, and then we add the value at the current index. So this is essentially what this first part of the code is doing. And then this second part is going to look a little bit more messy in Python, actually, because the index here goes from 0 to so let's just do like input 2 is equal to input 1, and then it goes from 0 to the length of input 2, but in increments of 2. And then the current value is, we treat this as a 16-bit number. And then, so because we can't like operate from these bytes, we convert those 2 bytes into a 16-bit number, and then we XOR it with this 1337, and then again we pack it back as a 16-bit integer. So now this Python code should do the same as the code in the binary. And we can actually test this by running this binary. Let me just okay, good. So what we want to do now is we want to set a breakpoint where this comparison is being made, or like when this is done. So at this address here, we want to set a breakpoint. But there's something we need to consider here. We see that in this case, this is a position independent binary. So every time you run the program, the code will be loaded in a different place in memory. So you can't just say, I want to set a breakpoint at this address. However, this Jeff extension has a way to handle this. So this value here is not like the absolute address in memory where the code will be loaded, but it's the offset relative to the base. But in Jeff, you can just say pi, instead of the regular GDB break, and then you would put the address. You can say pi break and this address. So now every time we run this binary, Jeff will like figure out where the program is loaded in memory, add this offset, and set the breakpoint in the corresponding position. So you don't need to like recalculate that manually when you run this. So we can then run this program, and then we can just input like A, B, C, D, E, F, G, H. Maybe it's like enough. We run this. Was there any other checks? Or did this not work? Oh, maybe. Wait, what? So can you make Gidra font bigger? Yeah, I think I can. It's somewhere here. No, I have done this. Think yes. I think this is. We go here, I think, and then we increase this, and then you do it separately here, I think. To this. Like this. So, yeah, please tell me if this is enough or if I should increase it even more. While I try to figure out why the break thing didn't work, that's very strange. Sorry, I'm just gonna cross-check that address and see if there's, or if like Kidra is like assuming certain base or something, and maybe because as I said, I'm not very good with Kidra, so maybe it's like, you know, assuming a certain base or something, and so this is Binary Ninja, by the way, another great reverse engineering tool. Okay, so it was as I suspected that they were adding, but this should work then. Let's just exit, TDP, pi, break, run. So why is this not breaking? Can we do even earlier? Let's go into the, let's start, we can do the entry break, or oh, okay, that worked. Maybe I had to run the start thing first, but I didn't think you had to do that. Okay. Anyway, let's get back on track. Remove all the breakpoints. We just do a break at this correct address, and then we I want to get rid of all the breakpoints now, and set okay. So we set the breakpoint to the debugger, and we get this. So I inserted my input here, A, B, C, D, E, F, G, H. So if we look at this location, so here you can see the program is actually like, the debugger actually, you know, figuring out, wait, it has the source code? Was this built completely with, or like, is it decompiling it? Whatever. We have the breakpoint here, and we have the call to memcopy. So we can just take those bytes in our input now, and we can see if our Python code produces the same result. So what you can do is we take this, or maybe we can actually, is it possible to do Oh, it even handles the variable name here. So we could probably do, we want to use the X to inspect the memory, and then we want to look at 8 bytes and 8 units of byte size printed as hexadecimal starting at input. So this is the result of the program processing the data. So we have this, and then if we do, if we provide this to our function, and then just print input 2.hex. So if we run our Python code, sorry, I'm in the wrong directory. And actually make the correct imports. We get this output, and we can actually make sure to compare this properly. So what we will do is we say that this is our target, and we will just print we will just say, are they equal? And yes, they are. Okay. So this means that we correctly implemented this kind of hashing function that's happening in the program. So now, as I said, there are 2 ways we can go about this. We could reverse this. So the way we would do this is we would take the target, the actual target from the binary. We would XOR this with XOR like every other, or each pair of bytes with 1337. And then we would undo this thing. The other way you could do it is, since that you know that like this, the last value, at most 2 bytes will affect each other from looking at this. You could just brute force all the combinations and build a table and like work it out. But I think we will actually do the thing where we actually like reverse the thing. So what we can do then is to grab the target thing. So how big is the target? Target length is hex 1A, which is 26. Yes. So we would do x26bx target, and this is all our target bytes. Actually, there is like a nice there's a nice function in Jeff to get this printed in a nice format. So you would do format is Python bit size 8 length 26. Yeah, so you should do like fpy b8 l26 and location target. Or do we have to do like p target? And now wait. Now something strange happened again. Oh, maybe maybe Jeff overrides the maybe I'm used to shortcuts that are overwritten. Right. And then we should be able to do just I guess we could just copy the address in directly. Yes, that worked. And you can even do then -C. Oh, okay. I need something that I haven't installed for this, but we can do this. So this is the buffer dumped from memory, formatted as a Python thing. So that's very nice. So this is the actual target. Hey, what happened? Oh, right. Copy pasting multiple lines in Tmux like this is not always great. So this is the actual target. Okay. So as I said, let's do this in reverse then. We take the target, which is input 2, and this operation is its own inverse. Like XORing with something, you undo this by XORing it with the same value again. So we can just copy paste this right away. And then input 1, so we're doing this backwards now. So input 1 is input 2. So now we need to do the inverse of this. So what is that? It's we subtract this from every element. So we move this around like this. It's still same one, and then we just negate this. So this should be the opposite operation. And then we could do, we print this. Input to target. All right. We need to create an actual byte subject out of this. Actually, a byte array object. And then, of course, if we subtract, or like this thing can wrap around. So we need to do this modulo 56. And something didn't work. So we made a mistake somehow. So let's see what we're doing wrong. This XORing should not be an issue. Let's see, did I actually copy like the whole thing? We can cross-check in Ghidra as well. We can see that it starts with, okay, it tries to format this, which is not great, but at least the fourth one should be 90. Yeah, that does not look correct. Was this like a signed, unsigned thing? No. It
shouldn't be. Or did we like dump the incorrect? Let's see. Data. So if we just put 6244. Because you copy the value that for the mem copy. There's no mem copy. This is a mem compare. Why is this? Is this actually? Yeah. Oh wait, no. Okay, I see what I'm doing. I'm not copying this. I think is the issue. We're copying the like where the pointer is located and not where it's pointing to. Yes, I haven't used this tool, so yeah, well, let's not do that. Let's copy it from the binary instead. I have to figure out what I'm doing wrong here. So let's just copy this from Ghidra. And then do this. Yeah, I mean, I know it. I'm not exactly sure what went wrong, but yes, this looks better. So I think I managed to copy the memory, like the incorrect values from memory, but instead we could go to Ghidra and take it out from here. And if we do this, we get this flag, your staff is broken, and then we can try this, and we see that we get this correct thing. So we solved the challenge. That's good. I need to figure out why this was not working correctly in the debugger. And then finally, we have the last part of this trilogy of reversing challenges called Barad-Dur. And we'll just close this one. And we'll do import file, go up to this one, to temp, open this file. Oh, this is if you run the file, you see it's also a 64-bit. Let's move this away a little bit. Clear file. So a 64-bit ELF binary. And if we run this, it says, "You fool, no man can kill me." And if we type something, it says, "Die now." Okay. So if we look at here we see a bunch of functions, which we don't really know what they are. Can't seem to find like a main function. So maybe this is then stripped. So we need to look at what's going on here in these different functions. Oh, there's some call to
ptrace here. Interesting. Okay, so this could be the main function, I guess. Right, yes, it is stripped. It says here, it's stripped. Thanks. So if we run this, without any input at all, you get this, you need to do something, which is printed here. And here we have the fget, and here we have this. So this seems like this main function, and this is a string, on like a stack string, and it's not like interpreting this correctly. But yeah, this is, you can see here that this is like ASCII range. So this is this message here. Okay, so what happens here? We have a call to ptrace here. And if it fails, it will print full and not run the rest of the program. So we can demonstrate what that means by running this in a debugger. Want to set up this redirection properly again. We can bring this out, and if we just run this, it will just print full and stop. So what happens here is that, so ptrace is the way you can do debug programs in Linux, for example. It's like the operating system interface. So you attach to another, you call ptrace to attach to another process, and then you perform debugging commands. But only one process can be attached to a process at a time. So what this program is doing is that it's using ptrace to attach to itself. So if you run this in a debugger, you're already attached to it in a debugger. And then if you try to run it, when the program tries to attach to itself, it can't do that because the debugger is already attached to the program, and it will fail and it will quit. So we need to, if we need to like be able to like figure out, I mean, we could do this fully statically where we just read the code and so on, but to be able to do like dynamic analysis on this, we need to kind of bypass this. So there's a few different ways you can do this. You could, for example, patch the code to just remove this call altogether. Or you could hook the ptrace function and make it return true anyway. And there are probably a few different other ways you can do this. But anyway, what happens if this succeeds and the program runs? It prints this, it asks for an input, it does this new line replacement thing. You see all these programs, they have a similar, very similar setup. And then let's see, where is the, yeah, so the variables are a bit strangely decoded here, but you can see that here there will be some shifting around of the data. You can see that it takes, like, it loops over the data and it basically rotates. You can see these operations like shift these things and order them back together. So you're just shifting each byte around 4 steps, or like rotating them around 4 steps. And then here, I think we have the same 1337 XORing thing going on, but expressed in a different way. And then some function here is called. And then there's a mem compare against the target. So this function will somehow, I guess, manipulate the data here. And what is this function? So this function, it will in turn call two other functions. And yeah, that's the stack cookie stuff. So we have a bunch of arguments. So in this first function here, we have some local variable. This is just an index. So now we can start renaming things. We just call this I. And this is... So here we're just setting up what you can see here. Like it takes a... it assumes that this is an array of 256 bytes, and it just assigns the index to each entry of this. And this is already pointing in one direction. So there's one very like there aren't that many situations where you would just want to create an array of 256 bytes where each entry is its own index. But there is a crypto function where this is like the first step of setting up the whole thing. Next thing, it will take this this table. So we can actually just call this like table 1 for now. And then you have here, it uses the other two arguments. So it will take, this is another index. We can call this like I2. So it will take an entry in the table plus some local variable plus an entry in this array. This is index, but modulo this parameter. So this is the length of this argument. So this is param1 length. Okay. This will create this variable, which it will shift. Okay, there's some like casting and shifting and stuff going around here. And what is this? It will do some stuff, these things, and then call this function, which is just, this is just a swap. You can see that like this is a temporary variable, so like it will move the param1 to temp, and then we'll move B to A and then temp to B. So this is a swap. How do I go back? Navigation. Previous. Okay. What's the shortcut for this? Alt Shift Left. Yes, because that's a reasonable default. Okay, so, but wait, why do we have 3 arguments to, can I do like, why do we have 3 arguments to a function? Oh, control up, is that the, oh, yeah, I'm, you know, you can see that I'm not really used to working with Ghidra, just fumbling around. So let's go back again. We were in here. Okay, so we are doing a swap here. And we do this 256 times. And then we call this function. So we have this parameter 1. And we call down here. And here is another call to ptrace, which is actually a bit interesting suddenly. And here's another loop. And we're doing some XORing in here. And so on. But I will, I can just jump ahead here a little bit and say, like, so figuring out what this is can be a little bit tricky if you haven't seen it before. But if you have seen this before, you will very quickly recognize the structure of this as the RC4 encryption algorithm. So let's look at how does the key scheduling algorithm works. You start, actually, let me increase this text size a little bit. You start by creating a table of the values 0 to 255 in a sequence. And then you loop 256 times and you do some swapping in this table based on this key. So this matches very well with what's going on here, right? You see, you set up the table here, you loop, I mean, there's a little bit of messy stuff going on here, but essentially you can see that you're picking out, so this would be the key, and this would be the key length. And we can edit. So key length would be like a size t, and the table, we don't care at the moment, but this would be like a char pointer. Can we do this? So now you start to see some stuff going on. So this table thing, we could actually also make this just like a char thing. And you can see how this starts getting more and more readable. So if we compare this to the article, this would be what they call J, this one. So let's call this J. And then I'm not sure though what happens here really. It's I think it's getting confused about like how they're juggling around these different, it's like some shifting around the different bits and stuff. I think this is just something odd the compiler did, but I think most of this is just a no-op. But you get this J, and then you do this swap here, and then you increase the index and so on. So this is the RC4 key scheduling algorithm. So, and then we can start making some educated guesses here. We said this thing here, the second parameter, that was this big table. So that we can call the RC4 state. This first argument here is the key. This is the key length. Okay, so these are two of the arguments to the function. And this then would reasonably be the actual RC4 encryption. So let's, first of all, let's just make that guess, go into this function, and what did we say? This was the RC4 state. And then these things are probably like plain text and ciphertext and length and something. For example, here, this seems like, since we use this as the limit of the loop, this would reasonably be the length. We should change the signature here. Even do like unsigned char. This. Okay, and we call this. Okay, they don't. I mean, here it's not stated in the same way, but and also here they kind of do it like this is how they generate the key stream, but in this function we also directly XOR with. So here you can actually see this. You see that parameter 3 and parameter 2. So here this will be super clear if we change the types here. Yes, thanks for reminding. I didn't update the status on the stream. That's fixed. It's good because the status thing, I also made sure to log the timestamps for these, so I will use this to generate like the timestamps for the stream, the description of the video later. If people just, I mean, I kind of doubt that people are gonna watch like the whole thing if they just want to look at like one specific challenge or whatever. But you can see here that this parameter 3 is the result of taking something from parameter 2 at the same index and then XORing with something related to this RC4 state. So reasonably, this is the output buffer and this is the input buffer. And yeah, so that's starting to look pretty good. So this would mean that what did we say? Input output length. So this would be the input output length. So now we have the full signature of this RC4 function. We have the key length, the input, the output, and the length. Of course, we're still kind of making some guesses here. Like we haven't fully verified that this is like actually RC4, but like it really looks like RC4. So we're just gonna, take a leap of faith here. So so what's happening here? We have this then would be the RC4 key. And this would be the RC4 key length. And okay, it's just encrypting in place. It's setting input and output to the same thing. And then this is the length of the input. So it basically seems that it's RC. So first, it's pre-processing the input a little bit, and then RC4 encrypting it, and then doing a comparison against a specific target here. So that should be pretty doable. Let's see. What's the fastest way to do this now? So we could do it similar to the previous challenge where we just implement this and in Python and like run it in reverse. I mean, we already have code for this part, and this is just rotating stuff, so that's fine. And RC4, we can just use a standard implementation. So we just need to figure out where this key is coming from. which we, for example, we could do. We could, yeah, decode this, or we could do it dynamically to see that that works as well. So of course, the way we would do this then would be to take the target RC4, decrypt it. And by the way, since this is a like a stream cipher that you just XOR with a key stream, encrypting and decrypting is the same operation. And this is why I called things input and output and not like ciphertext and plaintext, because it depends on what you put in the input. So we could decrypt the target with RC4 and then run it backwards through this. So yeah, let's combine some dynamic and like static analysis by just grabbing the key in this location and then doing the rest statically. So this call here is this address. So we do, oh no, yeah, we have to take care of the debugging issue here. Let's see, which, can you do patching in Ghidra? Patch instruction. Yes, okay, so we can do this. So what's the easiest way here? I think we could just flip this or we could just nop this instruction. So basically, so the return value of a function is stored in x86 by convention. You have the return value in the EAX or REX register. So if we just wait, why is it? Yeah, so what's doing it? You call ptrace, and then you check the REX register if it's an error, and if that's the case, they go into this branch. So there's a few different ways we could do this. We could change the value they compare it to. We could flip this jump to always jump. So now it says like jump if not 0. So we could just make, so I think that's the easiest thing. We just patch this to always jump over this. So patch instruction. Okay. This processor received a rating of gold during testing. Well, thanks, or good job, I guess. So we just changed the JNS to a JMP. So we still make the call to ptrace, but we don't care about the result. So now how do I do a save as here to apply the patch? Is that how it works? Or is that just the analysis? Let me where did this go? Or is it export? Is that how it works? Let's try to run this. No, that's not how it works then, I guess.
How do I actually apply the patches? Hydra patch binary. Patching a binary, saving the patch. So I need, okay. Okay, so you can't really do this out of the box. So we need this script. So we download this script into the Hydra. Where do you put this? Scripts directory. Display script manager. Manage script directories. Home Hydra scripts. Oh, you can create a. You can just have Hydra scripts, and then we download this here. And I guess I have to. Oh, you can just refresh it directly from the program. At least I thought I could. Did I misspell it? Hydra scripts. Let's just restart the program, I guess. So this one we can actually delete. So and we start Hydra again. And we open the Code Explorer again. Wait, did I accidentally? Oh, right, because I saved as and then I deleted. Oh, yeah, okay. I just lost all my naming and stuff. That was a bit stupid of me. Okay, now that works. Save patch is there. So usage, make changes, select the patch and run. Yeah, select the location for the change file. Yes, check the result. Okay, reasonable. So we have to go again to here, and then we go to here. We patch this with their gold rated thing. And then we change this to a jump. And I guess we can like select this and do run the script. Do we go here then and just run script?
running. Select output file, and then we go to the projects. And we call this the same, but patch, save changes. And now here we can have this patched binary, which is working. So if we run it in the debugger, so we don't get the full output, so we can debug it. Great. So we need to okay, so now we just need to add the breakpoint, which is down here. This was the RC4 function. So at this call, we get this, and then we can do start pi break this, and then just continue, and then we can input whatever. And then you see what we have, this call to this function. And the first argument here, can we just see which? Yes. So the first argument in x86 64-bit by convention, you have the first argument to the function is in the RDI register. So you can go to like x86 calling convention, and you can go to like the Wikipedia article, and then you can go down to like the 64-bit one, or like you can go down to this table, and you can see here you have these are the arguments. You put the first argument in the RDI register, so that's the one we're looking for. So we can see here that the arguments are like this, and it seems that they are actually using the "you fool, no man can kill me" string as the key for the RC4 encryption, and the first 1E characters of them. So let's get to solving this then. This is the RC4 key. And then the RC4 key length was 1E. And we need to so we import the RC4 algorithm, and then we also, of course, we need the target data. So this is what we want to get. So we copy that from the binary as well. Just keep interesting stuff. The target is this byte sequence, And then we can steal this part from the previous challenge because it seemed like it was identical. So the only thing now we need to change is, first of all, we need to actually RC4 key, and then the input 2 is the arg4 decrypt of the target, and then the XORing. And now we need to do the rotation of, so Python is like a nice yeah. Oh, so more subscribers, welcome. Okay, so we need to do for every element, we need to do a rotate so we do, because this thing here is a, what is this? We shift the, I mean, okay, it's by 4 steps, so it doesn't really matter which direction you rotate, but this is a, yeah, so we can just rotate left by 4 steps. So we rotate these values. Oh, there's just a bunch of subscribers dropping in. So it's we rotate by 4 steps, and it's an 8-bit value. And then we should be able to just print this. Oh. Okay, we did something, but it failed. So let's try to see what's going wrong here. We have the RC4. This looks a bit strange. 5A should be the first. Why did I get the 0? Okay, I did there was some copy pasting error, so it should start with 5A and then 9-1. Yes. So let's try it again. Oh, okay, and now this, that makes sense actually. So we still have an issue, but something that's kind of encouraging is that we expect the flag to start with 2 characters of the same type, and we have here 2 characters of the same type. So at least that could be indicate that we're going in the right direction. Let's check. We are getting data here. Yes. I mean, the rotation is, it shouldn't really matter. Like if you're rotating an 8-bit thing, wait, it shouldn't really matter, right? If you rotate 4 steps, it doesn't really matter. which direction, but wait, maybe I'm printing. No, okay, it's already. Is this? Maybe it's doing something more in here actually. So let's look at this again. Oh, okay. Yeah, I was sloppy here. So it's not just XORing with this 1337. It starts with that, but then you see it updates the value. So we have to go backwards. So they start with 1337, XOR that on the first 2 bytes, and then they take the result of that and they XOR the next 2 bytes with that, and they take the result of that and XOR the next 2 bytes and so on. So we have to start at the end and like I think, and work our way backwards. That would be the correct way to do this. So we can call this like XOR key, which would be okay. So probably like the last 2 bytes might be, could possibly be lost here. Yeah, this is like, this makes it a little bit more messy, but no big deal. So we'll do the key will be, so if we start at the end -2 and we go down to 0 in increment of -2, and then we actually start another 2 steps back, and this is the current value, and then the XOR key is like previous value, which is like the next value in the thing, and then we probably have to make another copy of this then to not destroy. So now the issue is that we probably need to, we need to start in the correct place, otherwise still this will not work. So would that be like another 4 steps back, or is it like another 6 steps? Yeah, no, that's let's look at the code again. this final thing here will oh, it also like flips. Okay, again, no, wait. No, okay, they are just in the in like shifted orders. I thought it was doing like every other byte or like swapping the positions, but you can see here that this one E1 is always like using the one that comes from the like index times 2 plus 2 thing. And this one here is always the index times 2 plus 1. So again, the last two elements in this array if you XOR that with the previous two in the target, you should get the plain text in that position. And then this is still, so we decrypt this target array, we take let's just print, just check that we're doing the right thing. Print this whole thing before we start, and also print print the two values that we are working with. So, maybe actually print two different things. B694. So we're taking the last value here. Yes, we are. And we're still keeping the actual like ciphertext. So and we should probably print this value as well. Okay, so no, there's something's going wrong here. We are, oh, this creates just a reference. We need to actually Python byte array copy. Can you do?
I can help reorder everyday items, track your deliveries, add to your shopping list.
No, Alexa.
Or answer
or yeah, so the problem here was that I made a copy of, or I thought I made a copy of the input to keep the like encrypted value throughout the loop, so I could reuse it for the next step. The problem was that I was just making a reference to the same array, so I was still overwriting the value, and then the decryption failed. Also, you see that this is stopping early, so I think we could do this. Or even this. No, but like you get it here. So the flag is I am no man. Or, well, the flag is potentially I am no man. So let's run this against the original binary, SSM. And that works. So that's the solution. Now, we completely sidestepped the trap in this challenge, which I will just quickly show you. So you remember how I pointed out that extra call to ptrace? So let's say you do patch away this call to ptrace, so that you can run it in a debugger. The program will run fine, no problem. But you are running in the debugger, so no, wait. Yeah, no, if you don't do the patching thing, if you do this thing instead, so let's say another way to go around this is to like hook the ptrace thing to always return true. The problem with that is then that inside this RC4 function here, we will make another call to ptrace, and if this call succeeds, it will modify these values that are used in the encryption function, and the encryption function will do a slightly different thing. So this means that if you hook the ptrace function to always return success, the program will behave differently, because the first ptrace call will return success, which is good because it will go through the exit thing. But the second ptrace call will also succeed, which will break the encryption. This because like this could not happen in a normal execution situation. The first call would succeed and the second call would fail. Now, if you patch the first one and run it, then it will be fine because, or rather, it will be fine if you run it in a debugger. Like the behavior will change outside the debugger, but you probably don't care about that. But inside the debugger will instead kind of do that first ptrace call, and then the second one here will still fail and everything's good. So that was like a small trick. So for hooking, what I usually do is use like LD preload to write a small shim. So it's pretty simple to write your own. If you want to look at a bunch of examples, there's a GitHub repository called Printf. So this contains a bunch of already pre-made hooks. So basically what you do is you create, let's pick a simple one, like the ptrace, like here. So you write a small piece of code like this, and you compile this into a shared library, and then you run your program and just like set this environment variable LD preload to the path of this library. This means that this library will be loaded before any other libraries. So and since the functions are named the same, the one that's loaded first will have precedence. So this Printf function implementation will be used instead of the one provided by the standard library. Of course, this does not work for statically compiled binaries where everything is baked into the binary. Then you would have to like find the functions inside the binary and modify it and so on. Okay, that's that. So that means we are done with these binary reversing challenges, and we have these other two. So let's go to the Verilog challenge, the Kodlock. So in this file challenge, first of all, let's update. So in this challenge, you're given these two files. So let's go into the temp thing, and we fetch that one and that one. Okay, so we have two files. We have a build we have an image and we have text. So let's look at the image. So this is like a schematics of a matrix keypad. So the way these works, you can imagine this is like being a part of a door keypad or something. The way it works, like to detect which button is being pressed, a circuit will output a signal first on row A, and not on any of the others, and then it will output the signal on row B and row C and D, and it will go back to A and so on. So it's like cycling through the rows, and at the same time it's listening for the signal on column 1, 2, 3. So like row A, B, C, D would be outputs from the circuit, and column 1, 2, 3 would be inputs into the circuit. Or you could do it the other way around, of course. So that means that, for example, if you are pushing down button number 6, the circuit will at some point output a signal on row B, and it will receive an input on column 3. So then it can deduce that you are pressing button number 6. So this is how this type of keypad works. So let's look at the code. And this is some Verilog code. So this is where you can program, you design circuits, and you can program FPGAs, which is kind of like reprogrammable hardware. So you define the behavior of your circuit. So it's like, connecting wires and stuff, but you're defining it in software. So we have a top module here where we have two components. We have a keypad and a lock. And this component defines a clock signal, a reset signal, input wires on column 1, 2, 3, and output wires on row A, B, C, D. So just like I described. And then an output register for the lock. Although this is actually a bug here. It should say output wire, but it doesn't matter. And here we're basically creating two components inside. So we have our main component, the main circuit, the code lock. And inside of it, we instantiate two components, the keypad and the lock. And then we connect the clock signal to the clock signal of the keypad, and so on. So we wire up this component to the inputs and outputs of our component. And we also have an internal wire. So you see all of these are wired to like things coming in and out externally. And then we have one wire, which this means that we have it's actually like 4 wires it's like a 4-bit value. So this wire is called key, and this is wired between the lock and the keypad. And then you also have these external things. So the keypad gets a clock signal, and it has these columns and rows, and it has this key wire that also is connected to the lock, and which also gets the clock and reset signal. And then you have the lock output here. So we have one component defining, like decoding the keypad, and one component defining the lock. And then we can look at the keypad. We can see here that it has this row select thing, which is a 2-bit counter. So it can count 0, 1, 2, 3, 0, 1, 2, 3. And then these are wires like just saying, you know, output the 1 on row 1, on row 2, and so on. So as this row select is counting up, one of these will be active at a time, like we described. And this is implemented by a counter here, and it says a mod n counter, and it's actually like if we jump down to this thing, it's defined down here. You can actually see that this is exactly what it's doing. It says like on every positive, like every time clock goes from low to high, if we have reached the maximum number, we go back to 0. Otherwise, we just increment by 1. So this is just a clock that cycles through a certain number of values. And then in this key scan thing, we have another behavior defined here. So we say that every time the clock goes from low to high, we look at the row select counter, and we say that if there are 4 cases. So if we are at 0, we are just starting like another scan cycle. We're going to go through all the lines and detect which row we are on. We will output the result of the previous like scan cycle out to the like output of this whole module. And then it will go through like if we are on row 0, and if we have input on column 1, then we set the scan key to 12. And this is where there's some slight obfuscation of the code. Like if this was reasonable code, this would be numbered like 1, 2, 3, 4, and so on. But yeah. So if we are in row 0, or that the first row and column 1, we set this value to 12, and so on. And then if we are at row 3 and column 2, we set this value to 6, and so on. So when we have cycled through a whole, so this value can be updated throughout the whole this whole cycle. But when we come back to 0, we actually set the output value of this whole thing. So we output the keypad key on this key wire. So that's when we actually update the externally visible state. So depending on what you're pressing, which button you're pressing, the key wire will be set to different numbers according to this. And the lock thing will just basically say that, you know, every time the clock cycle goes from low to high, if there was a change in which key was pressed, like if there's a new key being pressed, then let's check. We have this state that we're checking. So if we are in state 0 at the key, and the key that was pressed is 5, then go to state 1, and otherwise go to state 0 because it was incorrect. And the same thing, like if we are in state 5, if the key that was pressed was number 10, then go to state 6, like incremented by 1. Otherwise, go back to 0. So if we press the wrong key, we will go back to state 0. And then finally, this just says that if the state is 15, then the output of the lock signal is 1. So we just need to figure out what these key numbers, what actual key they correspond to. So we see that when we are in state 0, we're supposed to press key number 5. But this is not the actual 5 key, like not the 5 button. It's the key that's labeled 5 by the keypad system, which is this one, which is row 2, column 2, which actually happens to be 5, but that's just a coincidence. So we can just write this down. We have the first key is 5, and then when we're in the second state, we want to press key number 4. So we go up, and key number 4 is here. It's in row 2, column 3, which is a 6. So we add a 6 to the output. And then you keep going like this. So key 6 is row 3, column 2, which would be a 0. 5, 6, 0, and so on. And I'm not going to do the whole thing. You just continue like that for those 16 things. And you see, we had the beginning correct, 5, 6, 0. And that will be the flag of the challenge. So yeah, feel free if you have any questions or so about this, just ask, or if I should go deeper on something and so on. So let's go for the final reversing challenge that we haven't done. And then I think that's actually a good place to stop, because we've been going on for 5 hours. So I'm starting to get a little bit, tired of speaking for 5 hours straight. So we'll do this one, and then we'll do a little bit of a wrap up for this time. And then maybe I'll do another session for the rest of the challenges. So this one was not called AVR in the competition. It was called Strange Code. So in here we get the these two files, firmware.asm and eprom.hex. So what is this? So firmware.asm, some kind of assembly, and then the EPROM is a text file, and this is a so-called Intel hex file, and this is, I don't know like the exact specification of this, but basically you have like an address here, and then a number of bytes here, and I think this last byte here is like a small checksum or something. So this is used for typically like programming firmware and stuff to different embedded devices and stuff. So it's like a nice textual representation of like code or data with like a small checksum added to it, and it can be like a compact way of expressing this, because these addresses don't need to be sequential, of course. So let's see what we have here in the code. So Here we have an include, which is good because this would give us an indication of what kind of device we are working with. M328P, 80 mega 328P is a processor. So that's what we're dealing with here. And so what is this thing doing? First, we have an init function, and then we have a loop function, and then there's a success function and a fail function and a halt function, and then there is some encrypted data here. So we need to understand what this code is doing. So this processor is an AVR processor. So it's an architecture. Small embedded device things of various types. Fairly nice to work with. I think they're like quite differing opinions on them. But anyway, so what you have with these kinds of devices is like memory mapped IO and like IO registers and stuff like that. So for example, you can have different things connected to the device. So for example, if you have just like a serial communication component, you could have like a register in memory that you would just like read and write to send and read data over the serial communication, for example. You could have like a whole bunch of, depending on the processor, you can have different types of these like peripherals, which are then mapped into these registers or memory and so on, which you can then manipulate from the code by reading and writing to certain memory locations. So another interesting thing about this architecture is that you have it's like a hybrid 8-bit, 16-bit thing. So you have these registers are different numbers, which are 8-bit registers. But then there are some registers called like X, Y, Z, and so on. And they are 16-bit register consisting of pairs of these 8-bit registers. So you can use the Z register in some contexts as a 16-bit value, and the way you would load a 16-bit value into this is that you do it as two 8-bit loads. So you take the upper and lower 8 bits of some address, and you like you do two instructions to load these values. So basically here, what's going on is that we're loading the address of the encrypted data into this C register. And then we have these, so these things are these like different like control registers and so on. So there's something going on here, and then we will get to that later, and then we'll see that there's a loop. Let's see, you have a jump to loop here, and you also have a jump to loop down here. So let's see. So depending on what's going on here, this could just jump around here, or it could go on down here. And then it does something. It loads some value into R16. And it also loads, like, you know, you see, we basically, what we know so far is that it's manipulating like the R16 and R17 registers. Something's going on here. And then down here, they load these two into another of these like control register, and there's something going on here, and it loads a value from this register into this, and it loads this value into 17, and then it XORs them together, and here it will read a value from the register, increment it, and like increment the pointer, and then like you put the value in R17, which you will compare against R16, and if they're not equal, you jump to fail, and otherwise you increment the R25 register, which is up here set to 0, and if it's 52, we jump to success. So it seems to be like it's doing a bunch of things, and then finally it's doing a comparison, and if the comparison fails, we fail, and if it succeeds, we get another iteration of the loop, and if we do 52 iterations of the loop, we succeed. So that's a good like rough overview of what's going on. So now we need to go into the specifics of what's going on here. So now we need to start looking up these different registers. So let's Google this one. UART programming. So there's different ways you could do this. You could go into like the reference manual and read exactly what each register is doing and so on. Or maybe we could see like what are these. That's what I did when I did the reference solution of this. But let's see what people are doing in like here. Here's like a nice summary of things. So the register we said is like this is so UART is this like serial protocol thing. That's, for example, like if you connect your device with a USB port to the computer, you can communicate over this. So this UCSROA is the control register A for this USART 0. That's interesting. So we load that into R16. And then we do SBRS, which I'm not completely sure I remember what it's doing. Skip if bit in register set. So basically we're saying that so this thing here indicates a position of a bit in this register. So let's say that this is 5. We will need to look up what it is, but let's say it's 5 here. So we're saying that if bit number 5 of R16 is set, you should skip the next instruction. So this means that if it's not set, we will execute the next instruction and we will jump back to the loop. So basically this little loop is waiting for this specific bit to be set in the control register. And this is the receive complete bit. So basically we're waiting for like data being available to read. So we're just running in a loop until there is data to be read. And then we could expect this to be the actual data. Let's see if there is. Yeah, so this is basically the C equivalent of the code we're seeing. Like spin in a loop until the receive bit is set, and in that case return the value in this register. So this will contain the input. So R16 is 1 byte of input sent over the wire. And then we load number 0 into R17. And then let's see, we have pairs of these SBRC and SBR instruction. So let's look that instruction up. Maybe even in here. skip if bit in register is cleared. So that means that if bit number 0 in R16 is not set, we will skip this instruction. And then so on for all of these others. And you have this SBR instruction, which is set bits in register. So this will set this bit in this register. So basically, this means that if bit 0 in R16 is set, we will set 0, 1, 2, 3, 4. We will set bit number 4 in R17. And then this goes on for this whole thing. So this is kind of like a bit substitution thing. Like for every bit in 16, if that bit is set, we will set a different bit in 17. So we're like translating from one to the other. Okay, so then we understand this whole bit. Yeah, you see, it's a lot slower reading code when you just have like this assembly and not like a full decompilation. So this means that when we get down here, R17 will contain like a transformed version of R16. So what do we do now? We set R16 to 0, and we write R16 and 17 to these two registers. So what are they? Let's get some Google results. The EEPROM, okay. The address of the byte you want to write, I guess it's read as well, is the EER register. If the AVR you're using has more than 256 bytes, the EEAR register is divided into like the high and low registers. So yeah, here we can see EEPROM read. So basically what I think we're doing yes, so this is like similar to what we're doing, but they only have 1 byte for the register, 1 byte for the address, and we have 2 bytes for the address. But you can see the similarities here. So we put the address in the R16 register, for example, and then you set up the address by writing to these 2 address registers, and then you set the read enable bit of the EEPROM, and then here they do the same thing here and get the data from that address and load it to R16. So basically this whole thing is like take the bytes in R16 and R17. Well, R16 is always 0, so it's basically take the address in R17 and read from the EEPROM at that address and fetch the result into R16. And then you load 69 into R17, and this is the XOR instruction. You XOR them together, and then you read from the C address, which is pointing to encrypted from, we know this from the beginning. You read, and then you increment that register. So this like repeated calls to this will be like a sequential read in memory. So you read this into R17, and you can compare these two. And if they're not equal, you fail, and otherwise it's fine. So basically, if we summarize this, it's like we get 1 byte from this UART thing, and then we do this like bit translate of C, and then we do this like, we use this as an address into the EEPROM. So we do like EEPROM read from this address. And then finally, we do like XOR this with 69. And then we do like, so we have this index like I equals 0. And then if this C4 is equal to this, or rather, if they're not equal, then fail. And then we loop this. So this is essentially what this program is doing. So now we just need to write some code to, because like this thing, you saw there was like a one-to-one mapping, so we can reverse this. And assuming, it's basically using here the EEPROM as a table. So assuming that every value only occurs once, then we can easily invert this as well. And then the XOR is also invertible. So all of these operations are invertible, so we just need to go in the opposite direction, and we can decrypt the file. So let's just save this as a small reminder. There is a Python library for reading these Intel hex files, because this is what we need the EEPROM thing for. So this is this EEPROM thing. That's the table that we don't want to read from. So what we want to do is to invert. So we can do, let's implement the like forward substitution for this bit thing. We have the result is 0, and then we do like if x so if the first bit is set, then so now we just need to copy these so we do okay, so this is the forward substitution of this, and then we can just do bit sub reverse would just be so we basically what we do is, because this is always 1 byte, so we'll just build a table of like a reverse lookup table for all the values of this function. So you see that, for example, to get value 16, you input value 1, and so on. So this is like the reverse lookup. So now we have that taken care of. And then we want to read this Intel hex file. So we have the Intel hex file. Where is the documentation for this manual? The reading data. Right. So we do this. So do we still have anyone in the chat? Or am I talking into the void? Yeah, we have at least one person alive in the chat. That's good. That's good. So Yeah, we have a couple of people in the chat. Great, nice. No, great to see that some people are still here. So what we do here is we create this Intel hex object, and then we read this Intel hex file, and now we can index into this. But we want to do like the same reverse thing here. So wait, can you do like, can you call this, or would you? I think you need to like dump it into a. No, you can. Okay. Can I get just the can I just dump this to a list? That seemed to be a bad idea. So what I want to do, I just want to dump the first 500. Oh, right. Maybe we can just do a slice. To bin array. Ah, okay. That was the function I was looking for. Excellent. Why is there... So can you do this then? Okay. So we will need that, because now what we're gonna do, we're gonna take the this encrypted value. We're gonna take all those bytes. We're gonna start with this encrypted, and we have this, and then we have each flag, and then for every byte in encrypted. So now we need to do this in reverse. So first of all, XOR with 69, and then we need to do like a reverse lookup here. So we need to find, so this is actually where I need all of this stuff, and then like EEPROM data is this. So basically, we just find where in the EEPROM is that located. So that's the kind of the reverse lookup into this table. And then we do this bit translate, which is bit sub rev for this thing. And then we append this to the flag. And then finally, we convert those flag values to a bytes object, and we print this. And it works. I'm just gonna not print that. So here, I don't know how to x86, but AVR is pretty simple. So that's the solution to that challenge. So yeah, that means we have solved all of the reversing challenges as well. And with that, we are going to wrap it up for this time. So yeah, are there any questions, comments, suggestions, you know, things, other ways you can solve these things, or anything you want to say? You know, please put that in the chat as soon as possible. So what we did today was the introduction challenges, all of the forensics challenges, all of the reversing challenges, 2 of the pwnable challenges. So we have left the web, the MISC, the crypto, and a little bit of pwn. So maybe we did like half of the challenges or something now. Yeah. So when will the other solution? So yeah, maybe Sunday or Monday, possibly. Like, I might split it up. Maybe do a little bit on Sunday and a little bit on Monday. It's a little bit exhausting, like, you know, going on for, but it's now like 5.5 hours straight. So yeah, that's something like that. I will schedule something and it will show up. So, you know, if you subscribe to the channel, and you will get a notification when I schedule the stream. So yeah, but yeah, thanks, you know, thanks everyone for watching. And, you know, if you like this, you know the drill, like, subscribe, etc. And yeah, so have a nice day, evening, wherever you are. And yeah, goodbye.